Oh, that SSXG logo is now official, is it?
It is official, yes.
No. Cool.
SSG stands for what?
Solar Stellar X-ray Group.
Okay.
Who came up with that? Was it
Probably Joy. I think Joy.
Joy or I forgot John's postdoc's name. Ah,
Yeah. Sorry to interrupt. Should we start? Like it's
Yeah. Okay.
10:35, Pratik.
Yeah.
yeah,
Of
Sure.
sure.
course.
Okay. So
Uh
I'm going. Mhm.
yeah.
Yeah. I can
So
start, Pratik.
okay.
Okay. So hello everyone, and welcome to this session on the heliospheric structure and transient. My name is Yogesh, and I will be chairing this session. So this session includes 10 presentation followed by the session summary, and if you have any additional question and answers. So we have a very exciting lineup of the speakers, and each speaker will get 10 minutes to present their work, and then that will be followed by a 2 minute of question and answer. And Pratik will be sharing one clock feature in the Zoom, and that can tell you that you can see the uh, clock in the top of the Zoom, right top, or on the screen of the Pratik. And after 9 minutes, it will have some small music, and then you can wind up in 1 minute, and then we can go for question and answer. So the first talk will be presented by Srijan Bharti Das, and he will be presenting strong prevalence of hammerhead velocity distribution close to the heliospheric current seat. And Srijan, you can start.
All right, I'll get started because we have very little time. So, hi, I'm Srijan. I'm currently a postdoc at the Center for Astrophysics at Harvard and Smithsonian, and I'll be talking about how we went about detecting these very exotic distribution functions around the heliospheric current sheet. So let's back up a little bit and talk about what is the main science question here. So fundamentally, if you just write out the mass conservation equation and ideal gas law, if you assume that it's supposed to follow a polytropic distribution, you'll come at this radial law of minus 4/3 exponent. That's how fast the temperature of the solar wind should decrease as a function of solar radii as it evolves away from the sun. However, that's not observed. So this goes back way back into like the 1990s, where if so people observed the Voyager, Ulysses, and Helios data, and they found that if you plot the actual data of temperature as a function of solar radii and the 4/3 power law, you see that clearly that the temperature is much higher than it's expected theoretically, right? So that means that something is not accounted for in the simple model. And that brings us to the point that we need to start thinking about the solar wind not as a fluid, but more as a kinetic process. And why is that? That's because if you consider typical solar wind conditions, and over here I've mentioned some numbers which is at 1 AU, but it's roughly the same, across the heliosphere. Uh, so you'll see that it comes out to be pretty much weakly collisional. So one of the parameters that you can compute is the mean free path. So the time or the distance before an ion has a collision with another ion. In this case, for protons, that's approximately a tenth of 1 AU, which is a massive, massive distance. It can also be converted into the collision frequency, and that turns out to be roughly, every 10 power 6 seconds, you're going to get one collision, which is indicative of it being highly collisionless. So this means that we need to start looking at the treatment not as a pure MHD fluid system, but rather at a more kinetic slash particle level. So the equation I've written here represents the Vlasov-Maxwell equation under no collisions. And you can, in principle, simulate this equation to find for every particle, how does it move in the velocity and physical phase space. So I've written here f of n is a function of not just position, but also velocity. So these equations actually reduce to the imaged equation if you assume that the plasma is highly collisional and it equilibrates to form Maxwellian distributions. So in principle, you can take that equation on top and take moments of it And the 0th moment is going to give you the continuity equation, which tells you the evolution of density. First moment will give you the momentum equation that gives you the evolution of velocity, and the second moment would give you pressure. And if you combine all of these, you're going to end up with the usual imaged equations. So this shows that the velocity distribution functions f is the fundamental quantity that we should be going after. If you look at solar wind velocity distribution functions, it's an entire zoo. So starting from Helios observations, which is shown in the top left, you can see that it's not really a Maxwellian, which is like a Gaussian in 2D space. It has a distribution which is the bulk, which is called the core, and then there are stragglers, which is at a higher velocity, which is called a beam. And you can see in all the other examples that none of them look like a Maxwellian or a Gaussian. They all have a very peculiar characteristic shape, and they change from one to the other. Why is this the case? Because solar wind is highly structured. And you can think about the VDFs, the distribution functions that I just showed you, as being the fingerprints of the plasma processes that are at play. In the cartoon image on the right, you can see the sun in a global minima condition where it's globally a dipole. And then as it stretches out towards further distances, you see that the streamer belts start forming these current sheets. So the largest current sheet in the heliosphere is the heliospheric current sheet, and that forms the separatrix layer between the oppositely directed open field lines. So that is one of the components of one of my title, right? So the other is a hammerhead. What is a hammerhead? A hammerhead is one of the more peculiar distribution functions that we found using Parker Solar Probe observations. So this goes back to 2022 when Vernero et al. Found these hammerhead shark-shaped distributions with not just a core, but also a very interesting, highly perpendicularly stretched beam that you see in this image. And it was found that these distributions actually resonate with right-handed wave modes in the solar wind. What does that mean? It simply means that it is a very strong source of free energy in the solar wind. So in order to study these distributions statistically, what we had to do is not just rely on manual techniques of finding them, but rather come up with an automatic way of finding whenever we detect a hammerhead. So on the left is the distribution by Vernero 2022. On the right is the same thing. It's sort of the conventions of plotting are flipped, but it's found by this software tool that we developed called HamPy. And it automatically classifies if it's a hammerhead, and if it's a hammerhead, then it forms a core and a beam, and then the gap between that is called the neck. And it's shown by 3 different colors. And the way we do that is pretty simple. And we have to keep it simple because we have to scan over 5 million events. And the idea is that if you form kernels, which is representative of a certain structure that you want to find, and you slide it over the image, exactly where those structures of importance are, you're going to get a peak. And in this case, it's like, the eye feature is trying to be detected. So for us, that's the neck, and that neck is given by these gaps that's formed between the core and the beam. And so what we do is along each of these theta lines, we sort of slide a one-dimensional kernel, and we end up finding these necks, which are shown in red on both sides in the image below. As soon as it finds a neck on both sides of the distribution, it flags it as a hammerhead. And then we do the rest of the statistical processes after that as a downstream task. So we also have an interactive tool where you can just click around, you load a window of time, and you click around and it tells you if it's a hammerhead or not. If it is a hammerhead, it colors it according to core, beam, and hammer. And if it's not, it just keeps it not colored or not segregated. So what do we do with this? We ran HamPy to detect hammerheads for the first 20 encounters of Parker. Sorry, not first, from encounter 4 to encounter 23. So 20 encounters total. The first few were looking at the solar minimum configuration. The last few were looking at solar maximum configuration. It's important to notice this because the heliospheric current sheet goes from being nearly flat in the solar minimum configuration to nearly vertical in the solar maximum configuration. On the right over here is the histogram of hammerheads overlaid on magnetic fields. Normally, the heliospheric current sheets on these magnetic field plots where it's radial components is shown by the polarity reversals. And if you go from top to bottom, you'll slowly see that the histograms start clustering more and more sharply around the current sheets, which are also more sharp because the current sheets become vertical. The previous image I showed you did not have the heliographic coordinates. This is the same thing, but plotted on the heliographic map. And you can see that Parker's trajectory is plotted as these blue and red dots, and they're colored according to the BR. And the black line shows the HCS. So for a solar minimum configuration, you see that it's pretty much all along the HCS. But if you transition to a solar maximum, you see that these hammerheads, which are represented by the green dots, start clustering around very sharply around the HCS itself. Sometimes you don't even need to cross the HCS in the in situ data, but if you're just hanging around the HCS itself, it starts detecting these hammerheads. I have, just for context, all of these for 20 encounters. We can take a look at this later if you want. But I also just want to quickly show that if you zoom into these time windows, you can see hammerheads not just around HCS, but also like CMEs. And some of you might identify this to be the Labor Day CME. And you can see that right around where the CME starts, you see a peak in the hammerhead detections occurring. That's the black histogram here. And where it again goes through the HCS at the end of the CME, you see the hammerheads bump up again. The same thing can be observed if you look at encounter 6 switchback patches. In between every patch, you'll see that the hammerhead starts peaking. And I'm going to stop here because I'm out of time, but the package is available as an open source software in Zenodo, and we have we have a bunch of exciting questions coming up where we'll use HampI. I'll stop and I'll take questions quickly.
Yeah, I think, thank you for the nice presentation. I think Sibotos have a question. Can you open your mic and ask Sibotos?
Yeah,
Or
sure.
should I be?
I just read the question.
Wanted to ask.
Yeah, I read the
Yeah.
question. It's fine.
So what is the physical process that can lead to these hammerhead distributions?
Right. So that is definitely one of the follow-up questions that we are investigating. In the preliminary study by Vernier et al., they found that the hammerheads were pretty coincident with the right-handed circularly polarized wave. And if you do a theoretical study of quasi-linear theory, you can see that the hammerheads basically extract, or the energy is extracted from the hammerheads and dumped into these right-handed waves and as they start growing. So you'll see these nice shapes of the extended beams being formed if you just follow quasi-linear theory and track the energy transfer from the hammerheads to the right-handed wave polarizations. But it's still going to be investigated in the future and established statistically. Yeah.
So anybody have another question, or I have one question for you, Srijan?
Go on.
So I have done some study about current seed, which is leaking the energetic proton and making some very huge beams. But I don't know that how a current seed can form these hammerheads. I know that hammerhead can form the right hand waves or like the left hand waves.
Right. Yeah.
But
Yeah.
can that release of the energetic proton make this hammerhead or not?
So
Do you
very
have
recently,
any
we
idea?
actually came across a study in the Earth magnetosphere community where they actually found similar hammerhead shapes, and this was back in I don't know, 2010s, I think, by Jim Byrne. And anyway, the point is that they postulated that if you basically apply the conservation, one of the conservations of single particle motion, you're going to see that the kinetic energy as it goes to the magnetic mirror of the X point, they start being conserved, and so basically the parallel kinetic energy goes to the perpendicular kinetic energy and it gets stretched. So because the HCS itself is also one of a similar configuration of a current sheet that you see in the magnetopause tail, it's possible that that's one of the reasons. But again, that we are writing up a proposal to understand what that is. But as of now, this was just like you detect hammerheads around the HCS, and that's completely unbiased at this point. Yeah. I don't know if that answered your question.
Yeah, I think Yogesh frozen. But Srijan, there is one more question in the chat.
Oh,
If you
okay.
can see. by Soumyaranjan. Soumyaranjan, would you like to
Yeah.
unmute and ask? Or
One of the plots he showed that the kernels are used to match features in the distribution. Do they need to be symmetric around the net? Excellent question. So we do impose a symmetry consideration because in SolarWind, VDFs are it's a good approximation to consider the VDFs to be gyrotropic. So they should be symmetric about the magnetic field. So in order to make sure that we are having a good conservative, robust detection of a hammerhead and not just spurious necks due to noisy data, we do enforce a symmetry consideration.
Nice, thanks.
Right.
I'm just wondering, I mean, since the velocity distributions around the HCS may not be as symmetric as one would expect, but since I understand, I mean, this
It
is
will
kind
not
of
be,
a
you're right,
property
it's
of.
not, sorry, yeah. I was gonna say it's not gonna be symmetric about it, but because there's a time cadence of particle collection by the electrostatic analyzers which measured these, and that time window is much larger than the gyro frequencies, which is why you basically accumulate enough to wash away the non-gyrotropic part.
Right, thanks.
Yeah.
yeah, great. I think there is some problem with Yogesh. He will join in a couple of minutes. Let's thank again Srijan. Nice
Thank
talk.
you.
Now let's shift to next speaker, which is Shivutos Bishwas. Shivutos, can you start sharing?
Yeah. So is the screen is visible now?
Yes, not in full screen mode.
Just a second. Is it fine now?
Yes, yes.
Yeah.
Okay, great.
Sorry.
So again, the drill. Oh, hi, Yogesh. Yeah.
Yeah,
So the
I'm back.
drill
Yeah,
is.
it's
Yeah.
yeah. Sorry. Yeah, go ahead, please go ahead.
Yeah. So just at 9 minutes, you will hear a music. So you have to wind up within a minute
Okay.
after that. Yeah, great.
Okay. So hello everyone. Good morning from India. Myself Shivutosh Bishwas. I am a senior research fellow from Space Physics Lab in Vikram Sarabhai Space Center here in Trivandrum. So before starting, I would like to thank Indus and the organizing committee to give me a chance to present my new ongoing research that tells about the multi-point observation of ICME turbulence at 1 AU that was during October 2024 extreme solar storm. So as we all know, it's not moving. Just a second. Yep. So as we all know that in 2024, there were two extreme solar events happened. One was May 2024, that was the famously known as Gannon superstorm, and that was the most strongest storm in the ongoing 25 solar cycle, and followed by the October 2024 storm, 10th October, that was the second strongest, and where the it casted a geomagnetic storm, and the DST, that is the geomagnetic intensity of the geomagnetic variations that measures that, it went up to went beyond 300 nanoteslas. In a previous study by our group, Smita Tampi et al. In 2025, we have showed that this geomagnetic storm that was driven by a single ICME, and which you can see in this. Let me just go with the pointer. If you can see in the panel, the shock and the sheath region and the magnetic cloud was well distinguishable. So it seems that it is a single ICME, and as you can see, the sheath region was very much turbulent, and we have showed in that paper that the most geoeffectiveness came from the sheath region itself. Although you can see the IMF BZ was sustainably negative in the magnetic cloud region. This has motivated us to further extend the study with the October 2024 storm to bring out the turbulence perspective into that, to investigate the turbulence in solar wind, sheath, as well as magnetic cloud. Then we found that at the L1 point, Sun Earth Lagrangian 1 point, there were multiple spacecraft sitting there, like from NASA's WIND, ACE, and DISCOVER, and ISRO's Aditya L1. So why not extend that investigation or study into a multi-point observation perspective? So our objectives are pretty much clear: to investigate the magnetic turbulence specifically and the properties in the ICME, solar wind sheath and magnetic cloud, and whether there are some spatial variations. If it is there, how it is actually how is the phases of the turbulence, whether it's a modified turbulence or it's a young turbulence and so on. People have done this sort of multi-point observation based on the radial alignment before, but this is in our knowledge one of the first kind that we have chosen spacecraft such that it actually smoothly around 80 RE. So let me go to the next slide. Moving forward, if you want to study turbulence, the first thing comes to our mind: what is turbulence? To give a brief definition, it's not a definition, it's a quote by Alexander Chorin, American mathematician. He said that to distinguish the distinguishing feature of turbulence flow is its velocity field appears to be random and varies very unpredictably, although the system does follow a special set of equations which are not random, that we now know it's a Navier-Stokes equations. So that is very interesting stuff. So we have a set of equations that is not random, but just a difference in initial condition make the solutions diverge in a very large way. So this is a picture I have shown, drawn by Leonardo da Vinci to conceptualize the turbulence. It's just a random motion and Schwartz in the velocity fields in a fluid. And to be specific in a physical context, you may say that if you have a system and in the system there is constant energy deposition, it creates the random fluctuations in the velocity field, in case of plasma, velocity, density, as well as magnetic fields. And it creates some vortices, kind of, or so-called eddies. And these eddies actually brings down the kinetic energy or the turbulent kinetic energy from larger scale to the smaller scales in the process of cascading. And in that process, there are three defined regions where the largest scale, the energy is deposited into the system. It's called a energy containing range. And in the smallest scale, where the energy is cascaded from the larger scales to the smaller scale, and finally went into the dissipation and turning into heat. In between the two scales, where the dissipation is not effective or it's not present, and the energy containing range is also not present, in that particular scale, that is called the inertial range, the eddies or the vortices, whatever, they cascades into self-similar structures into smaller and smaller scales. This phenomena or turbulence, as we all know, that doesn't have any specific analytical theories or models mathematically. Kolmogorov did a dimension analysis with some simplistic assumptions like incompressibility, homogeneity and isotropy of a hydrodynamic fluid or a neutral fluid. He came up with a relation that the spectral density of the turbulent kinetic energy, it falls off as k power minus 5/3. That is famously known as Kolmogorov's universal law, where k stands for the wave number, the wave vector. It's actually, if you inverse that, you will get the spatial scales. In case of magnetohydrodynamics, you have magnetic field in it, which adds up a more complexity. And in magnetohydrodynamic case, Hiroshnikov and Krishnan just modified the Kolmogorov's law by imposing some imposing some extra parts that will come up in the next slides, and show that this scaling law can change and vary as k power minus 3/2. And in case of plasma, the vortex concept that we have, the shores of eddies, that no longer exist. In case of plasma, we know there are a lot of plasma waves exist, like Alfvén waves. Then along the magnetic field, there can be compressive waves like magnetosonic slow and fast. So these sort of waves, when they interact, they can actually lead to the cascading of the turbulent energy. Let's quickly go through the results. So what we did is, in this 2024 October storm, at the L1 point, around the L1 point, there are 4 spacecraft. Wind discovered ACE and Aditya. ACE and Aditya was at the dusk side with respect to the magnetosphere, and discovered in wind on the dawn. Dawn side was ACE and Aditya, and dusk side was wind and discovered. And the farthest separation between wind and Aditya was around 880 Earth radii, and which is pretty small compared to the astronomical scale of the ICME. And we have used the magnetic field data the highest resolution possible. For ACE, Aditya and Discover, it was 1 second data. And for wind, we have used 90 millisecond high resolution magnetic field data. Going to the magnetic power spectrum, as we can expect, this is a pretty expected plot. As you can see in the solar wind, and the sheath turbulence is highly elevated, as we can expect, because the ICMEs generally propagate with a very supersonic and superalbanic speed, and it causes ICME in front. It causes a shock, and that shock actually compresses the downstream solar wind, and it creates a very highly turbulent region with elevated density, elevated temperature. So the turbulent power is pretty much expected to be high, and the upper limit of the frequency is actually calculated from the Nyquist criteria. And in the magnetic cloud, as we know, the magnetic cloud is a slowly moving and smoothly moving magnetic field with high intensity of magnetic field, and generally we don't expect the turbulence to be pretty much higher than the sheath. But still, there are 3 such signatures where the turbulence power spectrum got very high. And the first, we'll come to this one by one, not to specific focus on the 3, but I can say that the first intense band in the magnetic cloud, it actually came from the ICME sheath and magnetic cloud boundary interactions. And the last part, it probably due to the reverse shock, and in between there was some discontinuity in the inside the magnetic field that can lead to this MC. Yeah, I'll just quickly wrap around. So going into the power spectral density, as you can see, all of this spacecraft that has distinctly different distributions and power spectral laws. I'll just quickly go to the table. As you can see in solar wind, the wind and Discover in the dusk sector, it cascades very steeper than the dawn sector. And in the sheath, the energy cascade is pretty much shallower than the upstream solar wind. That actually tells that the shock is actually giving a lot of energy to the system, and it rejuvenates or make the turbulence very younger in the sheath region. Magnetic cloud, typically we expect Kolmogorov's law, it is already there. But this sort of asymmetry is not expected in the full, when we analyze the full system as a whole. So we have gone into turbulent power anisotropies, as everybody knows that. If you just resolve the magnetic field into parallel perpendicular directions, and you can actually introduce a ratio called R, that is alpha per parallel by alpha perpendicular by parallel, just to see how much is the deviation or how the different slopes are acting differently. Like compressible part and the incompressible part. Compressible part is the perpendicular to the magnetic field that is mediated by Alfvén waves, and the incompressible part is due to the parallel to the magnetic fields. So what we found interesting is that in the solar wind there are.
Can you wind up in 1 minute?
1 minute? Yeah, sure. So in the solar wind, what we have noticed is that in the wind and Discover part, that is the dusk sector, the solar wind turbulence was much developed rather than the ACE and wind sector, ACE and Aditya sector, that is in the dawn sector. In the sheath region, the spectral density, spectral slope was extremely shallow. That gives rise to a young turbulence and fresh injection of energy due to shock interactions. And in the magnetic cloud, we generally see Kolmogorov's law, and it is like a developed turbulence. But once you go into deep inside the magnetic cloud, there can be some regions where there is enhanced dissipation due to some discontinuities or multiple interactions of CMEs that can actually lead to different characteristics of turbulence that you can see from here. We have chosen 2 regions, region 2 and 1. Region 2 has higher compressibility, like this we have shown. The compressibility factor in the region 2 is pretty much higher. So that comes to a conclusion of I'm coming to the conclusion is that if we do this azimuthally separated spacecraft analysis of turbulence, we can actually tell about that there are significant variations of these ICME turbulence properties in all the 3 regions, sheath, upstream solar wind, as well as magnetic cloud. And I can only fit a specific sheath turbulence characteristics here because it's a one single picture, and because sheath was mostly turbulent, so I have done that. So this manuscript is under revision, and I will happy to receive suggestions to further improve that. You can go through the archive link to further details into the paper. Thank you so much.
Tibotos, you have 2 questions in chat. I think to keep time in mind, I will just go for the next presentation.
Yeah, sure.
And there are more questions. We can take them in the later time.
Okay.
Yeah. So
Okay.
next we have Asis, and I think
Yes.
Asis is there. Can you share your screen?
Yes, yes, yes.
Can you go to the full screen mode? Yeah. So it's not in the full screen mode.
Okay.
No, it's good. Yeah. So next we have. Can you just go?
Is
Asis
this
Kumar
visible, sir?
Gupta. Yeah, it's
Yes.
visible now. So we have Asis Kumar Gupta from Department of Physics, Patna University, and he will be presenting the role of elephant wave in solar wind dynamics. So Asis, go ahead. And
Yes, sir.
one
Good
more
morning.
thing, you will be hearing small sound after 9 minutes left, and you can wind up in that next 1 minute. Okay, go ahead.
Okay, sir. Good morning, sir. We will present our work, the role of Olin waves in the solar wind dynamics. These are our outline of our presentations here. They are the just introductions slide here. Just basic introduction about the Alvin waves. Alvin waves, their nature is the transverse and incompressibles propagating on the magnetic field lengths. They are the equation directly related to the density. And they are the dispersion relations, omega squared just equal to kz square b squared, and they are the Alvin Mach numbers that define the two category of Alvinic waves, sub-Alvinic waves and super Alvinic waves. Now we discuss about Alvinic resonance. Alvinic resonance where the fast magneto-acoustic waves can convert into the shear Alvin waves at this resonance point, where the shear Alvin waves make this condition omega is equal to ba kz. The PUW mates basically they have two categories: kinetic Alvin waves and inertial Alvin waves, having the dispersion relationship over here, and inertial Alvin waves their dispersion relation this here. So kinetic Alvin waves are basically forward wave natures and that elliptical polarization there. They are the dispersion relations graph of kinetic Alvin waves, inertial Alvin waves vary with the wave numbers and frequency. This is the second subplot where the Alvin speeds versus the plasma density over the solar atmosphere. This is the reflection point where the Alvin speed get the value 892.1 kilometer per second. That the reflection point where the energy accumulates and dissipates. They are the solar wind and magnetic field dynamics this is the Fourier condition here. In the cylindrical coordinates, we have show the azimuthal magnetic fields that related to the solar rotations and the plasma velocities. These are the angular momentum flux through the cylinders of height 2 hours. This is the negative sign here because the Cartesian sign conventions here. So angular momentum flux through this cylinder getting these relations, and this is the mass flux where the mass flux relationship that is constant, and dividing the torque by mass flux, we expression dividing mass flux we get these relations. So we put this value Alvin wave speed Alvin we put these values VRs and then get these relations. That is very important. This is the angular momentum loss provided by this Alvin radius. This is the fractional mass loss to solar rotations, and getting these values total angular momentum divided by the angular momentum loss point mass. This get these values 0.06% of the sun mass need to be lost to hold its rotations. This is the next slide. This is the solar wind oscillation via Allen waves. I will show there. I show here there are some gravitational parameters and the density and pressure profiles. This is the mathematical profile here. This is Alvin speed profile here. And using the Alvin wave equation, this is the magnetic flux. This is the Alvin wave equation. This is the velocity fluctuation and the magnetic fluctuation relation here. That is very important to understanding how the velocity and velocity and magnetic perturbation is responsible to solar wind oscillations. These are the second order differential equations here. This is the radial force due to the wave equation that comes from the linear momentum equation, having the three terms here. The first term is the pressure gradient. This is the centrifugal force terms. This is the magnetic tension terms. And here this is the mechanism here, the how solar wind oscillation works. This is wave generation, that is the convection motion and connections of the lower solar atmospheres. This is the We have reflection point here. This is wave trapping regions. This is the energy equipment. Then the gradient of pressures that drive the solar wind oscillation. These are the mechanisms to understand how the solar wind oscillations towards the Earth atmospheres. These are the profiles here, the mathematical profiles of luminous speeds. Here the luminous speed that traps at this reflection pointed. Sorry, at this reflection pointed wave is trapping here, and then wave is time energy equivalent, and then due to gradient pressure, gradient magnetic pressure gradient, and travels towards it. This is the atmospheric density profiles here over the heliospheric distance, how the atmospheric density drops off its over the heliospheric distance. This is trap wave oscillations here over the phases, different this around this reflection point, and oscillates outwards towards the LSA outwards vary with the heliospheric distances. This is another plot. This radial oscillation. There are two kinds of follow is here, inward flow and outward flow around the reflection point due to the gradient wave pressure gradients. This is the models, Parker's hydrodynamic models, having some consumptions and governing these equations, momentum equation, continuity equations follow it. And the some solution of these Parker mathematical solutions that these are the normalized variables, and getting these relations, this key equation, this is the, and having the some singular points, right? So this is the master equation governing this flow. At this point, the flow speed just equal to the local sound speeds, having the two type of solutions, subsonic breeze and supersonic breeze. And these solutions are here. This is the Parker spiral angles. Tens I just did these relations here. In our Earth cases, the Parker spiral angle is about 45 degree or 135 degree. And also confirm the Poisson condition, the Coulomb parameters. They are the solutions. Here the some plot, they are having the some initial temperature here. This is the initial temperature. Our the initial temperature having highest initial temperatures have the highest Kelvin speeds, and lower initial temperature have the lowest initial speeds, Kelvin speeds. So around this orbit, this is the solutions of the sonic to supersonic regions, supersonic speeds around these critical points. This is the Parker spiral angles around or spiral angles about the Earth about the Earth 45 to 145 degree. So this is the observational intelligence. We have focused on the two kinds of spacecraft, Parker solar probes and the solar orbiters. Detects the pervasive large temperature galvanic switchbacks, turbulence structure in the heliospheres. Both kinds of sphere that confirms the galvanic fluctuations and turbulent structure within the heliospheres. We are the galvanic turbulence here. This is the magnetic fluctuation spectrum. Fluctuation at alpha, their value lie between the 1 and 2, and these are the line 1 and 2. This is the simulated observation and theory that is fitted with these relations, and their solar is getting their solar fitted, so 1 minus 1.6, that means 5 by 3. And this is the residual analysis of percentage plus 15% to minus 15% here. This is the LA solar orbital data, galvanic turbulence here. This is the red lens. This is the radial magnetic field lens. This is the blue line, the tangential magnetic field lens. This is normal magnetic field lens. The radial magnetic field lens, we have shown that we see that the radial we see that the reversible of magnetic field lens. Due to the reversible of magnetic field lens, some turbulence and some switchbacks is there around this across this reversible field lens, that evidence to turbulent is develop inside the within the heliospheres, right? This is the same things here. This is the field reversibles is there across across the cross helicity ones, and due to the field reversibles of magnetic field lens, some turbulence structures develop inside the heliospheres. This is the another Parker solar probe spacecrafts having the showing the same things as this is the magnetic field reversible here. Due to the magnetic field reversible, some turbulent structure develops inside the heliospheres. And this is the second subplot. This is luminosity. This is the across this cross helicities. Because this cross some switchbacks is there. Some switchback is there and regular wind are there. That means the turbulence structure found inside the heliospheres. These are the mechanisms that connect with the aluminum waves. So basically, two kinds of mechanisms. We have the fusion absorption and phase mixings. What is the fusion absorption? Absorption basically the global shearing waves, global shearing aluminum waves that propagate to the boundary mode conversion is now started to kinetic aluminum waves and hitting the ions. This is the making of unit absorptions that is responsible to how this molecule hitting the plasma ions. This is the second mechanism, the phase mixing, where the shear aluminum waves trap into the go into the transverse aluminum speed gradient mediums, and then develop the large land gradients and triggers the dissipations and heatings. These are the two kinds of mechanism that understanding the how the colon heating connection via the aluminum waves. This is a space where the application that this is the web solvent trap solvent interact with the both socks. Then after get the energy stored at the magnetic tails, then a connection is happening here. For the connection events that release the energy. They are the mechanism that results in the they due to the solar wind effect results in the geomagnetic storms, storm aurora, and GPS and power grid disturbances. So all waves are central factor to solar wind oscillation and
Assis, can you wind
heatings.
up in 1 minute?
The conclusion point is here. Aluminum waves are efficiently generators, and these waves are transports energy, carry the energy and momentums. Radial gradients in density and magnetic field that causes the partial reflection of aluminum waves, leading to the aluminum turbulence. Wave gradient pressures that contribute to oscillations of solar wind, and the some are yes. The overall the aluminum waves are the central to solar wind dynamics. Thanks. Yes, sir.
So anybody have any question? So if anybody asked before that, I have a one question for you. Like, as is now the Parker Solar Probe have crossed the subalfinic region, and we have observed solar wind in subalfinic and superalfinic region. So have you checked the forward and backward moving waves in both the region with the observation and with, I think you're using some
Yes,
model
in
or
the
something?
observation, the some field and reversals are there. We have found the field events and see the direct marks of the galvanic turbulence, and
Mm.
that means the two kinds of progression, inward and outward progression of this relation. That is directly evident to the theory, our theory, Parker solution.
So I just want to know that like how much by amplitude or let's say by energy have you compared with your model or waves?
Energy and momentum.
Yeah, like just how much energy they carry in your model or how much they carry in the like the observations.
So basically, turbulence factor that then the power spectrum density. That is the
Mm.
power spectrum density we have shown the that means the alpha factor depending the spectrum index. Okay, now so how they
Okay.
align with theory. This is the main things. Turbulence power spectrum
Okay.
that get this.
Okay. Thank you. If nobody have any other question, we can go to our next speaker. Kishore, can you try to share?
Yeah, 1 second.
And Assis, can you unshare the screen? Stop
Yes.
sharing. Yeah. Thank you
Share.
for that.
Is it visible?
Yeah, can you go in the full screen mode?
Yeah, 1 sec. Okay.
Yeah, so
So
Kishore will be presenting the characterizing alphanicity and proton temperature distribution in ICM magnetic cloud. So Kishore, you can start.
yes, okay. So first of all, thank you for giving me this opportunity to present my work. I am Kishore Kumbar, a PhD scholar from the Department of Physics, University of Mumbai. And today I will be discussing on the characterization of alphanicity and proton temperature distributions in the ICMA magnetic cloud. So our story starts with Alphen waves. As now since Ashish has given a brief description of Alphen waves, so I can slightly go ahead that we know that alpha waves are the fundamental MHD waves which are oscillating at low frequencies, and by nature they're transverse oscillation that propagate along the magnetic field lines where the magnetic field provides the restoring force. So these waves are usually observed in the in situ data by observing well correlated changes in the velocity and magnetic fluctuations. For example, maybe 1 second, I will use the pointer. Yeah. So for example, this particular plot shows the correlation plot between the velocity and the magnetic field in the alpha velocity unit. And you see the higher the correlation, more we see it is morely inclined towards the alphinic nature. And additionally, on the nature of the direction of propagation,
We classify alpha waves into two types. That is, one is the outward alpha waves or the anti-sunward alpha waves, and another one is the inward alpha waves. Whereas outward alpha waves are usually said to be formed from the solar origin, and whereas inward alpha waves are said to be non-solar, having some kind of non-solar origin. So these two modes of alpha waves are very much important for observational perspective or studies, because these two modes contribute to several physical processes such as the turbulence, plasma heating, plasma acceleration, as and even some studies suggest that they contribute to the space weather effects. So along with this means correlation plot between velocity and magnetic field, we also use the LCSR variables to determine the direction of these two flows. That is, we use this particular relation where z plus minus represents the direction of the outward and inward waves with respect to the background magnetic field, and delta V and delta V represents the fluctuations in the velocity and the magnetic field, again in the alpha and velocity units, where this is given by this particular relation. And using LCSR variables, we basically derive something called as a normalized cross helicity, which is an ideal invariant of MHD equation. Or this sigma c basically tells us the degree of alphanicity. That is, if sigma c is equal to +1, we say that there is highly chance of having outward alpha waves. Whereas if sigma c is equal to -1, we say it is inward alpha waves. I'm sorry, forgot to put it, but when sigma c is equal to 0, we say there is no alpha wave. So, moving ahead, these waves, as we all know, they are ubiquitous in nature, and they are observed in several space plasma environments, such as the solar corona, coronal loop, solar wind, Earth's magnetosphere, and even in lab fusion plasmas. And on one such environment in which I am particularly interested to observe these particular waves are the coronal mass ejections. As we all are aware that these are huge clouds of plasma, which is emitted from the sun's surface, and once it is expelled, it travels in the interplanetary space and can cause several space weather effects if it encounters Earth's magnetosphere, and thus it is considered as a major driver of space weather. So this coronal mass ejection, or CM in short, has an interplanetary counterpart, which we call as the ICME, or interplanetary coronal mass ejection, which is basically exhibits three-part structure. That is, it exhibits a leading shock front, where we usually observe the enhancement in all the plasma parameters, which is then followed by a turbulent compressed region called as the sheath region, and then which is followed by an order closed magnetic structure called as the magnetic cloud, which exhibits features such as enhanced magnetic field, decreasing velocity, number, density, and temperature, since it is an expanding structure, and most importantly, low plasma beta. So now, since past, there have been several studies which have observed these Alfvén waves within the ICMA magnetic clouds. So several of them have been done by our group, where we even observed them in the clouds, the sheath, as well as we observed their kinetic counterparts within these ICMA magnetic clouds. And there are other groups which have observed them in the sheath. So now question arises, since there have been several studies, so why I am even interested in this particular structure if already people have done a lot of studies within this? So first and most important motivation for me was that these magnetic clouds, they serve as a natural low plasma beta environment. Basically, these environments can be used to study different plasma heating theories, and maybe if we do some analysis within this environment, we can transfer this idea or whatever results we got within this to some other models for or other observations for other low plasma beta environments. So other apart from that, there was one observation by Feng and Wang, and of course by Lee et al. In 2016 and 17, where they observed some localized enhancement regions within the ICMA magnetic cloud. Now, this localized enhancement of the temperature was surprising. Why? Because our ICMA magnetic clouds, or in general ICMA, they are expanding structure. So you typically don't expect this kind of localized enhancement. So these localized enhancements suggest that there is some underlying heating mechanism. So what they put as an argument that maybe the CME or the ICME basically takes it these enhanced localized temperatures from the point of its origin. That is, it is carrying this temperature enhancement from the source, that is from the sun. Or maybe they suggested that okay, if not from the sun, maybe it may be because of the some internal process such as magnetic reconnection, which is happening inside the cloud, because of which there is some localized enhancement. Or the third mechanism which they supported or suggested is by the distribution of alpha. So this brought my interest for conducting this particular study, where we basically estimated the alphanic fluctuations, both inward and outward, and we tried to quantify like how much is the percentage of these fluctuations within the ICME cloud, because they contribute to different sub-processes as we discussed in the start. And we also tried to check like how much is the contribution in the temperature distributions, because as these alpha waves usually then don't dissipate, or no, sorry, not dissipate. They don't directly contribute to the plasma heating, but if they cascade to the kinetic domain, then they can lead to wave particle interaction, and they can further dissipate and transfer the energy while heating the plasma. So, keeping in this mind, we particularly consider this study where we took data from the wind spacecraft uh, spanning from 1995 to 2024, where we analyzed 474 ICME events, for which the catalog is available on the NASA's website. And we use 3-second data from the MFI and 3DP instrument, using which we first of all characterize the alpha and velocity, and then we estimated the LCR variables. Now, using LCR variable, we were sure that this is the direction outward and inward wave. But then we went ahead and we estimated the normalized cross helicity. Now, we estimated the normalized cross helicity using wavelet analysis. So, why wavelet? Because we were interested in the frequency as well as temporal domain. And since wavelet gives access to both of this, we use this. One of the another reason for this is because your alpha waves, they are usually lie within the frequency range of 10 raised to minus 1 to 10 raised to minus 4 hertz at 1 AM, and we were interested within that particular band of frequency. So once estimation of sigma c was done, we took a mean of this frequency band for each data point, and then we took a distribution of all the clouds. Now, before I show you the distribution, there was one question like, how do we even differentiate like which is outward or which is inward, or how do I say this is non-alphanic? So for that, we put up one particular criteria on sigma c. We said that if sigma c is greater than 0.5, we will call those data points as outward alpha, and if it is less than minus 0.5, we will say it is inward. And if it is in between them, that is between plus minus 0.5, we will say that is non-significant alpha or maybe no alphanic flow. So after implementing all of this, we got this particular distribution. Now on the y-axis, it is the occurrences for all the clouds, and this is the sigma c on the x-axis. So first of all, important feature you can see that the sigma c distribution is not symmetric in nature. It is asymmetric, with more shift or more skew towards the outward alpha side. And additionally, we observe a peak around sigma c equal to 0, which suggests that more data points may be around non-alphanic behavior. So this dotted line represents the thresholds which are put in our analysis. And from once we implement the threshold, we observe that around 74.68% of the data points exhibit non-alphanic behavior, whereas remaining 19.93% exhibit outward alphanic behavior, and 5.93 exhibit inward alphanic behavior. So this suggests that around 75% of the magnetic cloud intervals have non-alphanic kind of nature, and remaining 25% are alphanic with more dominance of the outward alpha, which is I would say more or less matching with the previous studies of imbalanced turbulence within the solar wind. Additionally, we also tried to check the temperature profile. So this is the temperature profile plot for the alphanic, non-alphanic, alphanic in outward, inward, and non-alphanic cases. And you can see from the left panel that the non-alphanic case has a more means higher distribution, which is expected because of large number of data points within that particular domain. And outward and inward is then followed by it. So what we did, we tried to normalize these plots. And once we plot the normalized distributions, we observe something interesting. What we observe that the maximum temperature for these peaks has different values. Like for outward, it is 4.5 EV, then inward it is 3.5 EV, and non-alphanic it is 3 EV. So it suggests that these three temperature distributions for three modes are showing distinct heating mechanisms. Additionally, one interesting feature you can observe from this is the yellow curve, which is for the non-alphanic distribution, acts as a baseline for the inward
So,
and the outward.
can you finish in
Yes.
1 minute?
Yeah, sure. Inward and outward. See, basically, we did a baseline subtraction and we got this kind of residual plot. So this residual plot, if we see that outward case, there is again maximum around 5.5 EV, and then it has small peaks around 10 EV, which diminishes around 15 EV, where we see a dotted line, and then it decreases till 20 EV, and then there is sudden enhancement, and which again goes till 33 EV, and then it reaches zero. Whereas the other case, in the inward case, we observe several peaks around 6 EV, 10 EV, then 12 eV, then 18 eV, and then again 20 eV. So this suggests that there are different mechanisms through which these two modes are contributing in the enhancement of the temperature. So on a conclusionary slide, basically, first of all, the ischemic clouds exhibit lower alphanicity than the ambient solar wind. The asymmetric nature of the sigma C suggests that there is a unequal distribution of the outward and inward populations within the ICM magnetic cloud. And the announcement showed that these two modes contribute max to around 15 eV and then up to max around 33 eV, till after which there is no contribution from these particular modes within these environments. And what we suggest that maybe since alpha and are not contributing directly, their kinetic modes may be contributing to the overall enhancement, but what mechanism is yet unknown, because this is a statistical study, and for that we'll have to do a single event analysis. So this is just a snapshot of the article which was recently published in the APGL. So I would like to thank our collaborator for constantly supporting our work.
Okay.
And thank you. Yes.
So there are
So
two
we
questions in the chat,
yeah.
two, three questions in the chat.
Okay.
I will go with the first. Sneha,
Mhm.
do you want to speak?
Should I
Yeah,
switch on to the 6 Zoom?
yes. So you showed the plot of occurrences versus the.
Yes.
Could you go to that slide? Yeah,
Yes.
the mountain thing. Maybe I answered myself, but you said it was some 400 something events, ICME events that
Yes.
you studied, and then these occurrences are in thousands. So I was wondering, is it the timestamps for like entire time frame of the one ICME, and then each timestamp you're calculating the parameters?
Yeah, what exactly we do? We basically take sigma C for all the events, and then all the events we took it together. In the sense, we just concluded all the events together, and then we plotted the histogram. It is like the occurrences changes depending upon the bins. So here we estimated the bins, and based upon that, it is happening. But all the sigma C values are calculated for almost all the points in the events.
Thank you.
Okay, so sigma
You
C
have
value is not for an individual ICME, but each
No, no.
timestamp in a given
Yes.
ICME.
Yes.
Okay,
Yes.
okay. Thanks a lot.
so I think you have two more questions in chat, and Pratik, you have haze rand or something.
Sorry.
So
No, I was saying the time is complete. So maybe
yeah, yeah. So you have two questions in chat, so we will go for the next speaker. Can you stop
Yeah,
sharing?
sure. I can address them later.
Yeah. So meanwhile, Komal, can you start sharing the screen?
Yeah, sure.
If the it is possible to connect compressible to
Can you
non-alpha.
mute Kishore? Okay. So Komal will be presenting a comprehensive statistical study of subalphonic intervals observed at 1 AU. Komal, go ahead, please.
Yeah, sure. Is my screen visible and am I
Yeah.
audible?
Yeah.
Okay, thank you. Okay. First of all, thanks ISHA, the Indus and Indus committee for giving me the opportunity to speak about my work. I'll be talking about the comprehensive statistical study of subalphonic intervals observed at 1 AU, and this particular study is carried out using the wind TDP data, 3-second data. Yes, this study I did with the Vagish Mishra and Somaranjan Khuntia. I'll be talking detail about the particularly on subalpinic intervals, what are those, then how did we identify that, and what are the processes and structures we are trying to see within it. So polytropic index estimation and then turbulence analysis, and also I'll conclude at the end. So what are the subalpinic regions? So when alpine speed exceeds the solar wind speed, so this ratio will give you the alpine Mach number, so solar wind speed by alpine speed. And when it goes below unity, this indicates the presence of subalpinic region. And one of the also characteristics are, so this is primarily caused by the extremely low density region and embedded within mostly ICMA magnetic cloud, and also the some solar wind region, and which is result from some of the overexpansion. So on the right hand side, you can see some structure like a ICME coming towards the earth here, and within that you can see some patches, white patches, Those are extremely low density regions. These are subalpinic regions. So why it is important to study? So subalpinic regions weakens the bow shock, enabling solar winds to reach Earth's magnetopause directly, and they are observed within the ICME magnetic clouds and high-speed solar wind stream. So on the right-hand side, you can see the Earth's magnetosphere, and here is the bow shock, either of created any of the major structure. So this is the scenario when without subalpinic region, and here you can see the almost absence of the bow shock and giving a direct access to the Earth's magnetopause. And this is the scenario in the presence of subalpinic regions. So the motivation and research gap, why do we need to study it and how it started? So when subalpinic regions are expected to occur more often near the sun, while it is very rarely occur near Earth regions. So as the solar wind speed is always high as compared to alpha speed near Earth, so it is very rarely we identify such events. So the previous studies have primarily focused on its identification. So you can see in Zhang et al., Usanova et al., and in my present paper there are many citations which majorly says like near Earth or near 1 AU. So most of the work regarding the subalpinic region has done on terms of its identification rather than what kind of physical processes are governing within it. So since they are overexpanding structures, it is worth studying their thermodynamic and turbulence property. So to address this gap, our research aims to investigate the thermodynamic and turbulence property of subalpinic regions at 1AU using in situ data. So we use the wind data, particularly GDP data, 3-second cadence. So the identification method, subalpinic regions are characterized by alpha and Mach number less than 1, and it's having very low plasma density. So we identified the 11 subalpinic regions within 1995 till 2023. So you can see here the bottom figure, the alpha and Mach number on top panel, and the bottom one is the density. So this bounded region is the subalpinic region. I mean, it tells the presence of subalpinic region. So here the alpha and Mach number goes below unity, and the plasma density compared to the neighboring part is very, very low. This is one of the events I have presented. So this is the entire ICM you can see where the red dashed line represents the onset of the shock, and the ICME magnetic cloud is, like, I don't know whether you can see or not, but this is the gray shaded region. This is the cloud region, and the pink shaded region represents the presence of subalpinic region. Where you can see, like earlier, is the Mach number is below 1 and density is very low, where the alpha speed is high and the solar wind speed is comparatively less. So this pink shaded region, now we are going to see more detail. So this is the pink shaded region, is for the event occurred on 20th March 2002. This is the subalpinic region. And we, for our particularly study for all 11 events, we have taken the approximately entire time interval of subalpinic region for its pre-subalpinic and post-subalpinic. So these pre and post are nothing but the superalpinic regions. So on the right hand side, you can see it's not the completely equal interval because of some other structures come here. So we truncate it up to this part. So here also all the plasma parameters from the magnetic field to solar wind, alpha speed, alpha Mach number, density, and temperature. So primarily you can see again like solar wind speed decreases, alpha speed increases. So leads to alpha Mach number goes below unity and density is very low. So this is the presence of the subalpinic region. So what we did, we applied the polytropic index estimation method. So for that, polytropic equation for the ideal gas is this, and its linear equation for this by solving it. So this provides the polytropic index, that is alpha. So this is how we did it. So we entire interval we did in a windowing it of a each window carrying a 5 data points at least. So this is one of the examples. So how will you get it? So this is one of the window where you can see the 5 data points, and it's the polytropic equation part. So this is a positive correlation where you will get, yes, and of course the criteria for having for this PC value correlation coefficient should be greater than 0.8. So this will give you either positive correlation or a negative correlation. What does it mean? So it gives for this particular 2002 event, the same event, we have done like 3 separated parts, like the subalpinic region is one and its neighboring region pre and post are the superalpinic. Here by applying the polytropic equation, we get 2 different modes. So this is kind of bimodal distribution. So is it something unique by getting a interesting part or something like that? But not really. Previously, all studies give such a kind of distribution, but their method was to either take a common mean for getting a polytropic index or applying a K-Gaussian or something methods to get it like this. But using this method, which is the only presently mostly accepted common method, that Pearson one, we use the same method likely previous studies used. But the only thing from our perspective, we give a priority to study it individually rather taking a common mean or applying a Gaussian one. So here we study it individually. So like you can see, there is a huge gap at the 1, and 1, it doesn't mean that there is nothing happening, or 1 means the isothermal process, but it's where it is absent in the nature, not at all. So it is not, it's the method that provides such a facility to study differently and the absence of the isothermal state. So we studied here, as you can see, this alpha values like polytropic index, as it moves ahead, getting the positive values, it means the subadiabatic to going adiabatic state, so which is providing a cooling effect. And then it is below 1, that is mild explosive to explosive process are happening, so suggesting or indicating a heating effect. So here, almost in every case, we get such a kind of 2 distributions, and we prefer to work individually, looking it at as a 2 different distributions rather taking a common one. So this is for the all events. This plot is for the left hand side, all events. So similarly sub to previous one, but that was only for the one event, and here all 11 events we have merged. So we get for almost all events such a kind of bimodal distribution, and here again we can see the adiabatic or subadiabatic processes on this part, and which is separated by this isothermal part, and then we have studied it using a multiple slope error, so that will remove mostly the error part or data construction and all. So in 90% of the events, we got a transition in the polytropic index, means suggesting the transition in states possibly in both in superalpinic and subalpinic parts. So you can see these median values of polytropic index are here. From this part you will not get to see it completely. In paper I have given a table properly where you can clearly see the change or transition in both the values or either of the values in superalpinic and subalpinic part. So, and almost all the events we get the polytropic index in a bimodal distribution. So there is one more thing.
Komal, can you finish in 1 minute?
Oh, sure. So here you can also see as we go ahead. So we can see here because of possibly a picker pants or something, polytropic index values are getting lower. So this is the super epoch, which is again tell you the middle one is the subalpinic part. So I'll skip this part. And the turbulence properties. So turbulence, this is the inertial range. This is the cartoon type of picture. We have also studied the turbulence. So this is the inertial range and dissipation range, and this energy containing range, injection range. So this is the method using the magnetic field fluctuation for the turbulence. And then this is one of the spectra for the same event, superalpinic and subalpinic. And these are the initial range and a dissipation range. So the turbulence spectra of the event, so the initial range, we have used this one for the initial, and 64% of the events show the steepest spectra, suggesting the high turbulence in the superalpinic region compared to subalpinic, where rest of the events suggesting that the turbulence in the subalpinic region is higher compared to the superalpinic one. Also in the dissipation range, so we see the marginally difference for the, that is close to 2.45 in a subalpinic and superalpinic. So the key takeaway are the transition in the polytropic
Komal, can
index.
you finish?
Yes, just a minute. So in the initial, so this is close to, in an inertial range, is close to Kolmogorov scale, and in the superalpinic region is having the higher turbulence compared to subalpinic. Similarly, in dissipation with the marginal difference. And yeah, thank you.
So you have a question in chat. I think you can answer that in chat. So
Yeah.
we will go ahead with the next speaker.
Okay.
And I think Sneha is the next. Can you start sharing? And yeah.
Yes. Can you see my screen?
Yeah.
Yes.
Okay.
Hello.
So,
Yeah.
sorry.
Sorry, go ahead.
So Sneha will be presenting the statistical study of the magnetic switchback in the solar wind. So Sneha, please go ahead.
Yes. Hello everyone. Thank you for the opportunity for sharing my quick results. I have kept the slides so that even master students can understand it. So it might be that initially a few minutes will be not few minutes, but a couple of slides will be a bit too trivial for many people in the meeting. So in the title, we have a word switchbacks, and I would just like to point out what switchbacks mean. These are sudden deviations or deflections of magnetic field in the theoretical or nominal Parker spiral direction. So for example, PSP, an in situ kind of probe, goes inside these structures, basically inside the core of the solar wind, very close to the sun, and moves through these structures. So what happens is, so this pink is our PSP, Mercury, Venus, and Earth. These are each encounters which we can see in this infographics, let's call it. So this is the velocity in orange and the distance from the sun in blue. And so these each encounter, like 1, 2, 3, and so on, is basically PSP is moving through the physical structure that we are observing. So the major difference between a remote sense data and in situ data is that the remote sense data is looking at the structure far away from it. So it's usually only changing in time and very less in space, because like Earth is quite far away from the sun. Whereas in situ data is changing in space and time at the same time. So for example, this is how the in situ data looks like, and this is how switchbacks look like. But the previous point is, so this each timestamp that we have is, so the information that we have, for example, for the velocity or for the magnetic field, is different in space as well as in time. So that is something very peculiar to wrap your head around. So that's the basic introduction. Now we go to the switchbacks. So how do they look like is, basically we have this kind of change in usually radial magnetic field and also other components of the magnetic field, accompanied by change in velocity. And it can be alvenic, it can be subalvenic, superalvenic, and so on. It can have accompanied variations in the proton density, helium abundance, because on board PSP we have only helium counter, but with solar orbiter we also have other kind of abundances that we can observe. It can have moderate to high density variations. It can have, for example, here the radial magnetic field is enhanced, but it can also have a drop, and so on. So we actually, one thing to note, Z is just the measure of deflection. So the angle alpha is the angle between the observed magnetic field and the theoretical magnetic field of the Parker spiral. So Z is the measure of the deflection from the theoretical Parker spiral. So we are going to use this quite a lot in the further of the talk. And then we can have strahl directions reversed or not. And there is basically very many kinds of switchback that we can observe. So there is very difficult to have a consensus on the definition of switchbacks. So what I have done is we have several encounters, but I've used first 17 encounters. So this each distribution is each encounter. What I'm showing is the value of Z throughout the encounter. So each dot is one switchback. We have distance distribution here. So firstly in Z, what we see is that the distribution is quite skewed. So this solid histogram is a logarithmic distribution, and the filled one is numbers basically. So the distribution of Z parameters is extremely skewed, and that kind of creates problems. We will deal with that a bit later. The distribution of distance is not that skewed. We have a lot of data at large distances and a few data also like comparable at closer to the sun. So the closest that we are at is at the 17th encounter, and that is 11.4 solar radii. And the farthest is also on the 17th encounter, that is near 60 solar radii. So that is the range that we have in distances. And we want to understand the dependence of solar events on the events happening in situ. So on switchbacks, let's say. So we are looking at the sunspot number. So this data is taken from SILSO. And for most of the switchbacks, we have very low solar activity. But eventually in 2022, the activity picks up. So we also have like a few data points with slightly higher solar activity. So that's the description of the data that we are going to use. One more. So here is where we are going to try and deal with the skewness of the distribution of Z parameter. So this is from the literature, and this is for only the first encounter. But what they find out is basically this is kind of a turbulence cascade. And what happens is the very small deflections, which are, let's say, Z greater than less than 0.1, we cannot distinguish that structure in situ from actual turbulence. So in literature, usually people do not consider these as switchbacks. So that is what we have done as well. So we are considering Z greater than 0.1 for our further study. So here we can see that the event counts, this is in log, and if we have like log-like binning for Z, we can see a similar trend, like, they are moving, they're changing with distance. Eventually, after large distances, we have very few event counts for almost all the Z bins. But with time, we do not have much of a trend. So to get that trend out, we do some statistical methods. So first thing that we do is we plot probability of Z greater than 4, or probability of large switch deflections with the sunspot number versus the distance. So we want to basically disentangle the effect of solar activity from the effect of evolution of solar wind with distance. So here what we see is we have a lesser number of large deflections with increased solar activity. So in each distance bin, when we are going towards high sunspot number, we have lesser and lesser number of deflections. At the same time, the probability of large deflections increases with distance. So in this direction, the color is basically going towards the higher value. We also constructed an indicator. We call it asymmetry index. So it is the normalized difference between small deflections and large deflections. Basically, we have very little amount of large deflections. So this should basically be called relative proportion of small deflections. So this indicator, if we do the same kind of plot with activity versus distance, we see that we have a consensus result that the amount of amount of small deflections basically decreases with solar activity, which means amount of large deflections increases with solar activity, and that is something we want to work with further. What we did next is to have this asymmetry index plotted at different distances. Yes, I will quickly finish in 2 minutes. So asymmetry index plotted with time, oops, as well as plotted with the encounter averaged sunspot number. So we see a positive slope in almost all the distance cases and all distance case as well. So it shows positive slope. We have basic dependence like on solar activity. What we want to do is to have more robust result for that. So what we do is we disentangle the individual contributions of distance and sunspot number. We do multilinear regression as well, and we find out that the sunspot number coefficient is always negative. We do different kind of multilinear regressions basically, and it shows negative. That means strong switchbacks, that the probability of strong switchbacks and the strength of switchbacks decreases with increasing solar activity. It is inversely proportional to the solar activity. And for the distance, we have positive coefficients with the multilinear regression. And that suggests that the switchback becomes slightly stronger statistically with increasing distance. So basically the structure, the plasma blob with slightly different magnetic field from the surroundings, that structure is going to expand. And if it is very small deflection, it is just going to, fade away with like mix with the surrounding plasma. Or if it is stronger, it is expand, and that's why we are going to have statistically significant positive dependence on distance. So these are the conclusions. So we have
I think,
successfully.
thank you. We
Okay.
can take a question and people can read the conclusions meanwhile.
Sure.
So I don't know who is SKS. Can you open the mic and ask the question? Or should I read? So the question is, can you elaborate on the different type of switchback?
Yes. Okay. So switchbacks can have, can I go back in slides? Yeah. Yeah, here. So I cannot point out anymore. Sorry. Yes, here. So this is a very idealized case where I'm showing a very clear change in the radial magnetic field, where we see a jump from almost near 0 nanotesla to almost 50 nanotesla. And sorry for that. So we see this jump, but it is not necessary to have like very clean structure like this, even in the radial magnetic field. So we can have incorporated structure within this. There can be a slight jump here or getting back here and so on. So within the magnetic field structures, we can have a different kind of occurrences. Similar thing can happen with velocities, with
Thank you,
with
Sneha.
yeah.
You can ask detail in, you can put detail in the chat, and there are two more
Yes,
questions
yes.
from Jubair and Kalpis. So you can talk in chat, or we can also take that question later stage.
Yeah. Can I ask right now, or should I ask in the discussion? During
So
discussion?
it will be good if you can go in the chat, because we are a little
Okay.
late in the time.
Okay. Yeah, we can discuss that.
So next we have Preetham Das. So Preetham, can you share the screen? Yeah, so Preetham will be presenting the CME kinematics with optical flow multi-chronograph insight into internal velocity dispersion. So Preetham, please go ahead. I think you are muted.
Yeah. Am I audible now?
Yeah.
Yeah.
Go ahead.
Okay, great. Hi everyone. I'm Preetham Das. I'm from Aries in Nainital. So I will be showing you my work on CME kinematics with optical flow, multi-chronograph insights into internal velocity dispersion. So let's begin. We already know what coronal mass ejections are or what CMEs are. They are major drivers of space weather. They can cause geomagnetic storms, which affect both space and ground-based systems. So on your right, you have a classical CME image with its classical three-part structure, the leading edge, the cavity, and the core. So this is what we used to know about CMEs, that this is how they look like. But in recent times, the picture has come out to be more complex. So this is one observation from Parker Solar Probe, and you can see there are actually even more complex internal morphologies inside them. For example, this is coronal loop-like structures that have been found inside the CME front, which means their internal velocity distribution still remains poorly understood. And this is because the typical techniques that we have to study the kinematics are either limited to tracking only the leading edge of the CME, or they are assuming certain geometrical shapes or velocity profile. So here in this table, I've listed some typical techniques that we have been using for studying the kinematics. So they are either only tracking the leading edge, or they are not giving us the complete velocity map of the CME, or they are not capturing the non-radial motion, or they are assuming these geometric or velocity profiles. So this is where our work comes into the picture, the dense optical flow method, which tries to tick all the correct boxes. Where, though I should mention that all these methods earlier have been instrumental for our current knowledge in CMEs. So let us talk about the optical flow method. So this is the theory about optical flow method, but I will not go into this jargon. Instead, I will try to give you a graphical demonstration of what optical flow method is. So let's say you have a CME on your left, and it is moving from left to right, and these are two pixels in your image, pixel 1 and pixel 2. So the pixel is so the CME is moving from left to right. So in the first frame, the first pixel lights up, and when the CME moves further right, the second pixel lights up, and this becomes dark. And this is what actually is happening. But the assumption of optical flow is that the intensity always remains constant, which means this is the pixel 1, and it is assuming that it is simply moved into this new location. So based on the time taken for it to do so, it calculates the optical flow. And this is, in a summary, what optical flow is doing. So the data we have used to apply our optical flow method is the two state-of-the-art chronographs. One is Aspix from Proba 3, which is a formation flying chronograph, which uses these two satellites, where one is acting as an occulter and one is acting as the observing telescope. The field of view and the data we have used is listed here. And for another one is Metis, a dual channel chronograph, which has both visible and UV channels. Now we have selected four CME events based on the following criteria: that it should be a limb CME event. The data should have cadence higher or greater than 2 minute, and it should have complete coverage when the CME is traversing from the inner field of view to the outer field of view. So based on that, we have four limb CME events. But now you all know that chronograph data are filled or dominated by noise because the intensity of the features are very low. So to highlight or to mitigate that, we have used running difference. But those who have worked with running difference images might know that whenever the difference between the running reference frame are too low, there is this dark artifact behind the trailing edge of the moving feature, which one might confuse as a cavity, but actually it might be a combination of both the cavity and the artifact of the running difference. But when the uh, time interval between the running difference frames are too high, there is this artificial broadening of the feature because of motion blurring. So we have tried to optimize this using a 2-frame interval, and we have verified it using the Metis UV channel, where you can see this is a prominence material, and the contour matches with quite great with the core of the CME here in this chronographing image. Apart from that, we have used spatial mask to cover the occulter area, and we have removed the invalid pixels. And finally, we have used exponential intensity normalization, which suppresses the noise, but at the same time enhances the bright features of the CME. Now, the story so far was quite good, but the aspects data has a very big problem. That is, it has a very micro level misalignment or jitter between the occulter and the observing telescope. As a result, you can see there is a lot of flicker around the occulter here. So to mitigate that, we have formulated and created our own Gaussian tapering Fourier filter. So what it does is, first we stack up all the images, and through all the pixels we have our time series data. And now we go into the Fourier domain and we try to suppress the high frequency signal, but we are not completely removing it, because removing it completely brings out ringing artifacts. So what we do is we put a Gaussian filter, which gradually suppresses the higher frequency, and this is the final result. You can see this is the flickering is greatly reduced in this filtered animation, but the features are also enhanced, you can see, which are not there here. So the flickering still present, but it is greatly reduced from the unfiltered one. So now that we have our pre-processing steps, we have this running difference image after the pre-processing, but it still has a lot of noise around the image. So what we do is we use a bilateral filter, which is essentially a Gaussian filter, but with the edge preserving term multiplied to it. So what it does is it blurs out the noise, but it then preserves the CME feature that we have. And then finally, we use our dense optical flow method or the Farnbach method on it, and we finally get this velocity map around the image. And then we simply overplot it on the chronograph image. And now all these vectors that you see not only have the magnitude of the velocity, but also the direction of the velocity vectors. Now, we also have some other thresholds to remove other glaring artifacts or noise in the image. Now you can see a animation of how this event looks with optical flow applied to it. Yeah. So now that we have our method ready, we need to validate whether it is even detecting the velocities correctly or not. So to do that, we take a slit and then we generate this height, time, or XT maps. And then we use a semi-automated peak intensity detection technique to track the leading edge of the CME here. And then we compare it with the optical flow method. So we take only those optical flow vectors which are here as that was being detected by the XT map, and you can see the temporal trends are matching quite well. So this was one. This was for the Metis event. For Aspix and LASCO C2 also we validated it, and you can see the temporal trends are matching quite well. So our results, final results was that for Aspix and Metis, the difference was about 11 to 13%, whereas for LASCO C2, the difference was 30%, obviously because of its poor temporal resolution, because optical flow needs good cadence. Now that we have a method, let's look at some analysis results. So we tracked different position angles using slits, and then around the apex of the CME, and you can see even across different position angles, the kinematics are differing quite a lot. And what interestingly we found is that I hope you can see this impulsive phase of the acceleration of the CME. So whenever there is this decay phase in the acceleration phase, you can see the height difference between the front and the core suddenly starts to rise up. It means whenever there is this impulsive phase of the CME, there was a lot of restructuring in the morphologies in the internal CME structures. This was also observed using a Metis event, where you can see around this position angle, the core was associated with the prominence, whereas for, I will finish in 2 minutes. So, and around this, we did not have prominence. You can see when the core had this impulsive acceleration, whereas the front did not, still we had the same result where the height dispersion increases. So the restructuring after the impulsive acceleration does occur. Here also we see the same trend. Here, this was a peculiar CME where the front, where the core eventually caught up with the front, where you can see the velocity of the core increases and it overpowers the front, and the same is also shown here, also visible in the height difference plot. Now that we have seen the velocity dispersion between the structures, What about the velocity dispersion inside or within these structures? So we have manually tracked this using using a lasso technique with coherent structures between the front, and you can see this is the velocity distribution of the different CMEs. Each column here is essentially a velocity histogram. So you can
Pritham,
see the core is more or less
can
moving
you
as a
finish in
coherent
1 minute?
Yeah,
Can you
sure.
complete?
So
Yeah.
the core is moving more or like a coherent structure, whereas the front shows a lot of dispersion. So we wanted to see where is the dispersion coming from. So we further segregated the front into 4 different parts: the front leading half, the lagging half, the top flank, and the bottom flank. So what we found is the impulsive velocity phase was actually contribution from the leading half of the front, whereas the lower velocities were the contribution from the top and bottom flank. So these are the conclusion and key takeaways. So optical flow does provide a reliable and spatially resolved velocity fields. And the front and core dynamics vary with position angle, and they'll show a lot of dispersion, which can only be resolved using techniques like optical flow. And one important result that we found is that height separation between the front and the core increases after impulsive acceleration that I've shown you. And it typically occurs between 2.3 to 3 solar radii, which is the middle corner regime. And future work involves getting the 3D velocity reconstruction, because optical flow gives you plane of sight. So we can use polarization technique to combine with the optical flow to finally obtain the 3D velocities. Yeah, thank you.
Any question for Pritham? So if nothing, so I have one question. I put it in the chat. So can we do this kind of study using the Aditya L1 chronograph?
Well, it depends. So for that, we need to first create image processing for VLC, because currently the VLC images that we have are using raster scan. We do not have the complete image of the VLC. We need to recreate the whole field of view, and it can actually take greater than 1 to 2 hours. So optical flow I think, will not work. It will give you poor results.
Okay, so I'm not expert in the field, so I was just kind of asking that can we do this or not? Yeah, thank you. So we have next speaker, Jyoti. Can you start sharing the screen? And meanwhile, Jyoti will be presenting first evidence for dual polytropic behavior in ICME structure in the inner heliosphere.
Can you see my screen?
No.
Okay. Okay. Yes, now it's possible.
Yeah, now. Yeah, we can see it now.
Okay.
Yeah, please go ahead.
Hello everyone. I am Jyoti Shoran from Aries Nainital, and I am working with the Vivek and Professor Dipankar Banerjee. And today I will be presenting our work in which we report the first evidence for dual polytropic behavior in ICME structures. And this work has been done in collaboration with Eva Weller, Emma Davis, and Christian Mossel from Austin Space Weather, and Vivek Menon, who's a undergraduate student at Department of Physics at ISC. So to start with, I will start with a brief introduction. So as you all know about CMEs, they are large-scale eruption of magnetized plasma from the solar corona into the heliosphere. And you can see a CME that is, in this movie, you can see a CME that is captured by Solasco C2 chronograph. And the middle panel is showing a schematic of this CME. So when this CME enters into the interplanetary space, we call them as interplanetary coronal mass ejection, or ICMEs. And this middle panel is showing the schematic of 3D structure of an ICME, and basically there are 3 parts. So if the CME is fast enough, it will drive a forward soak, and which you can also see in this movie, and it will accumulate and compress the plasma ahead of it, which will form this turbulent sheath region. And this helical magnetic field topology region is the magnetic structure of the core of the CME, and which is basically a flux rope. So, and this region is called as the magnetic ejecta. And the right panel is showing the in situ data of ACME that is captured by solar orbiter on October 10th, 2023. And the shaded gray region is showing the sheath. And if you look into the in situ in the magnetic field and plasma signature, you will see that this region is highly turbulent, and the magnetic field is showing highly fluctuation. You will see a rise in velocity, high density, high temperature, and plasma beta greater than 1. And this blue shade region is showing the magnetic ejecta of the CME. And in this, you will see a enhancement in the magnetic field. You will find the rotation in the one of the component of the magnetic field. In the velocity profile, you will see a smooth decline in the from front to back, which basically shows the expansion of this ejecta region, and it has low density and very low temperature, and basically the plasma beta is very low in the magnetic ejecta region. So moving further, like a subset of this magnetic ejecta, which contains a single flux rope. In that, you will see a smooth magnetic field rotation up to a very large angle, up to 180° in at least one of the component of magnetic field, and you will see low plasma beta and reduced proton temperature and density. So these type of ejecta are known as magnetic cloud, and we can use Lundquist and Goldhuis solution of basic equation of MSD to describe such kind of magnetic cloud. Uh, but a subset of magnetic flux rope, which we cannot be reproduced using force-free models or more advanced reconstruction technique, they are known as magnetic cloud-like ejecta. So what are magnetic cloud-like ejecta? Is basically they are the ejecta which will show all of the signatures similar to this magnetic cloud. But if we look into the magnetic field, we can divide it into two parts. So in the front part, you will see that magnetic field is rotating and its magnitude is declining. But in the back region, the magnetic field remains stationary and its magnitude remain almost constant. So this back region of this M-cell ejecta has puzzled the researcher for long, and there are basically two possible explanations that has been existed in the literature. One is that these M-cell like ejecta are basically due to geometrical effect, and Mossel et al. Showed that this M-cell signature structure can be a consequence of spacecraft passing through the ICME flank. The other possible explanation that existed is that the magnetic declination at the front of the ejecta, it can change the magnetic topology, and which can give this back region. So in this figure, you can see the cross section of this flux rope. When this is non-eroded MC, you will find that the azimuthal magnetic component is symmetric about this MC center, and this red curve is showing the accumulated azimuthal magnetic flux, and it will go exactly back to zero at the end of this magnetic cloud region. But if there is a reconnection at the front of this ejecta, it will erode this cloud, and it will change the magnetic topology, which will result in the variation in the azimuth component of magnetic field. And you can see that the accumulating azimuthal flux will go back to null value before reaching the end of the magnetic cloud region. So they propose that this kind of magnetic reconnection at the front, they can reveal this back region in which we cannot see any rotation and the magnetic field is remaining constant. So in this work, we studied an ICM event that occurred on 23 to 24 March in the year 2024 using a readily aligned multi-spacecraft. So this ICM is listed in Helio Forecast catalog, and this is captured by solar orbiter, stereo and wind, which are in radial alignment. And the right figure is showing the in situ observation of this ICME at solar orbiter. So if we look into this magnetic ejecta region, this uh, magenta dash line is dividing it into two regions. So in the front region, we can clearly see that this is showing the rotation, the magnetic field component are showing rotation, and the magnetic field magnitude is declining. But in the back region, we see that these components are stationary, and the magnitude is almost constant. And the other signature, you can see smooth decline in velocity, low temperature, and very low plasma beta, which are basically this MC signature. So this shows that this ejecta is a MCL-like ejecta, and this gray region is showing the sheath, and this purple dash line is showing another possible discontinuity that might be present in the sheath region. So these are the in situ observation of the same ICME at stereo and wind, and we find that the CME is the ejecta is showing its MCL signature at stereo at mid location also. We trace back the CME to see near cell counterparts. So we see that we find that this CME has as a consequence of two CME that occurred near simultaneous, and we can see that there are two CME front, CME1 and CME2 in this stereo core 2 field of view. We also look into the source region of these two CMEs, and we find that and there is a active there is a flare for happening in active region 3614 that result in CME1, and the same flare triggered the eruption of a filament whose one leg was routed into the same active region, and it was extended northeastward, and it begins to erupt, and it gives rise to the CME2. Moving further, okay, so this CME is also listed into Donkey catalog, which provides us with the CME kinematics, such as it provides us its propagation direction, its speed, and half width. So we use these parameter as input to perform evaluation, and which is shown in this video. So here this blue semicircle are showing this two CME front of CME1 and CME2, and we can see that these results are matching closely with the okay, and this right panel is showing the in situ signature at solar orbiter, stereo, and wind, and we can see that our results are matching closely with the in situ signature. So looking into the simulation, we can see that all of the three spacecraft has encountered near apex region of these two CMEs. So we conclude from here is that MCL-like ejecta, they can arise from the interaction of two closely spaced CME when they are sampled near their apex. So, and there is one study by Lucas and Farguia, which based on MSD simulation, they also propose that there can be MCL-like signature resulting from CME-CME interaction. So this event kind of provide the observational evidence support to their studies. So moving further, we studied the radial evolution of these ICME parameters. So I will not go into each one in detail. So I will point only the main result. So first is we studied the size, how the size of these ICME sheath and mantle ejecta is varying with radial distance. So we find that the sheath is expanding at a faster rate compared to the ejecta. So this is basically due to the snowflow effect. So it is means that in addition to the intrinsic expansion of the sheath, there is accumulation of solar wind plasma. So that is giving rise to the faster expansion of sheath. Further, we find that in the sheath region, the magnetic pressure and thermal pressure, they are reaching at nearly the same rate. And while in the magnetic ejecta, we find that the magnetic pressure is decreasing at a
Jyoti,
faster rate
can you finish
compared
in
to the
1 minute?
yes. Yeah, just 2 minutes. Okay. Sorry. Then the thermal pressure. So moving further, we also determine the polytropic index. So which is basically we know that for an ideal proton population, we can write it in terms of thermal pressure and proton density. And if we write this equation in the logarithmic form and we perform a linear fit, we will get the proton polytropic index. So this figure is showing the distribution of log P versus log N, and we can clearly see that in the magnetic ejecta and sheath region, we can clearly see there are two distribution of proton population, and this sorry, the color of this data point is marked according to the observation time. So we then perform an F test to determine whether this distribution is better described by single single slope or double slope. And so we find that this is best described by two slopes. And we also determine the optical transition time at which this population is changing from one polar tropic index to another polar tropic index. And the same is done for stereo and wind. So what we find is that the optical transition time for the sheath region is coinciding with the closely coinciding with the time of the discontinuity that is present in the sheath. And for the ejecta region, we find that this time is coinciding with the onset time of the back region of the magnetic ejecta. So this tells us that these two distinct population in this ICME sheath and ejecta are caused due to the CME that is these two CME that is introducing plasma of different origins and heating history into the magnetic ejecta. So as we see that one CME1 is due to the flare and CME2 was due to filament eruption. So we can see that there are clearly distinct different in these two polar tropic index. And for the
Jyoti,
sheath
can
region,
you
it
finish
basically
it?
yes, I'm going to the concluding slide next. Okay, so in the sheath region, we can see that it is representing the disturbances like that are collected by the both two CMEs. So okay, and same we see in the wind also, but for the wind, we do not find any analogy between this optical time T1 and this onset time of that region. This tells us that there is an ongoing mixing. So this summarizes the result. So this single fit is showing if we fit only a single slope to this distribution, so this is the value of polar tropic index we will get. And that result is showing how our two slope model is describing compared to our single slope. So we find that in every region sheath and ejecta region, our this distribution is better described by two slope. And if we look into this the values of the polytropic index, so in the sheath region you see there is a distinct difference into the values at the near sun also. And if we go to higher distances also, we see that this difference is maintained. So this can be explained in terms of this pressure. So we found that like in the sheath region, the pressure is decreasing at the magnetic and thermal pressure, they are decreasing at the same rate, which may help to preserve this thermodynamic contrast at larger distances also. But in the
Yeah.
ejector region, if you look into the values,
Jyoti,
in near sun, we see
Jyoti,
there are two values. Yes, this is the last slide. Okay, okay, yeah.
yeah,
There are two
thank you.
values. Uh, uh, I'm sorry. There are two values, distinct values. One is closer to isothermal, one is closer to adiabatic. But if we go to at larger distances, we find that two values, there is very slightest difference between two values, and these two values are also equivalent to the single fit. So this
Okay,
tells us that,
thank you,
okay,
Jyoti. Sorry
uh,
for that,
uh,
but you
yeah,
have two questions in the chat. You can answer
yes.
those. We will go for the next presentation by Vasant. Vasant, can you please share your screen?
Yes, I can share my screen.
Okay, and Jyoti, can you unshare your screen? Just do the stop share. Yeah. So Vasant will be presenting tracking the slow solar wind from 1 AU to its source region using multi-vantage point observation. So please go ahead.
Yes, I can go ahead. Thank you for organizing this uh, meeting. And I'm Vasant Anand, and I'm a second year PhD student at Royal Observatory of Belgium, as well as at KU Leuven. So I mainly work with Yasmina and Merlina from the institute. They are my supervisor, and rest of them are my collaborators. So let me go. Let me start with the basic introduction about the solar wind, and then I will go into my research. So, what is solar wind? Solar wind is a hot supersonic flow of plasma and charged particles from the sun, which flows into the heliosphere. And basically, we know that solar wind is classified into two basic categories. One is the fast solar wind, and it's coming from coronal hole, and the other one is the slow solar wind, which is coming from large scale coronal structures, and some more structures are there. And the properties of the fast solar wind and the slow solar wind differs significantly. This indicates they have like different sources, and they are coming from different regions in the sun, and it also comes from different processes in the sun. So based on that, but my focus is on about mainly slow solar wind, and the origin of the slow solar wind is a little bit not well understood, how it is coming from the sun and all. So, what are the limitation in understanding about the slow solar wind origin is how these slow solar wind are ejected from these large scale structures, how these closed field lines are opening up and releasing the trapped plasma as slow solar wind. And also there is observational limit between the EUV and white light observation. This leads to observational gap, so that it become difficult to track them from one UV to white light observation. So this can be overcome with our new high resolution, and has a wide field of view resolution of a solar orbiter through FSI instrument, and FSI telescope in EUI instrument. So, and there is also different mechanisms involved in these slow solar wind origin. Basically, from the review paper of Luciabo in 2016, has a brief study about these mechanism, and also recent papers like Pradeep Chitta et al. At 2022 discuss about how these low solar wind streams are ejected from these large scale coronal structures. So based on these studies, I used FSI 174 angstrom data to observe and collect large scale structures in the year 2022. So these are my basically my four large scale coronal structure, like cusp, cavities, and coronal fan and complex structures. So I basically look these kind of structures in the FSI data through JHelio viewer and track them. So I used like 1 hour cadence data, and I collected like 44 events from January 2022 to October 2022. And I made a catalog with different parameters such as duration, width, height, and based and several more other columns. And I implemented some statistical study on these parameters. But let me show a pie chart which showing like different a number of structures in different categories. And so also I added some more observations corresponding to FSI from different wavelength. It's UVI from different instrument, UVI from stereo A, and swap from proba 2 to collect the same duration, to track the same structures in different from different instrument, from different vantage point. So which gives you the same structure which is viewed in different time, so that it will increase the probability of the duration of the structure. So if the duration of the structure is more, you can analyze the structure in more detail. Also you have like multi vantage point observations. And based on the parameters which I have collected, I did some statistical study. Here you can see like different circles has different numbers. The numbers represent the total the number of total structures in that category. So in the x-axis it's the duration in days, and the y-axis is it's the width. So width represents uh, the angular width of the structure, how wide the structure it is, or how big the structure it is. So, and the different colors represent the different structures. So I implemented this DB scan clustering to see how the scatter plot clusters into different groups. So this is like a very less data points for the study, but still I implemented the clustering technique and verified with the student t-test that it gives like three different groups. One group it's stretching from here to here like a lower width and has a wide range of duration, and there is a second group which has like higher widths but has a low duration and mainly populated with complex structures and cusp. And in the first group it is populated almost like all the four structures, and these three are like it's in the middle, has like medium width and but has a long duration. So they are two cusp and one coronal fan, and there is one outlier. Then I went to compare the duration, the observed duration of these structures from different wavelength. So each of the color represent it's the duration, observed duration from the different instrument. So this observed duration varies with respect to the instruments because of their different viewpoints and their speeds and their instrument sensitivities. So then I moved to the in situ part to see what kind of where what are the intervals where I can find like very slow solar wind for my analysis of finding its origin. So I used I start to use the in situ data from L1 point wind and A spacecraft. So for wind I used 1 minute cadence, and A's I have like 2 hours cadence data. So basically, these are like a few parameters I used in the in situ study. So I marked different ICMEs and in the in situ plot, and also with the ballistic mapping and also comparison with the parameters, I marked the fast solar wind also. So there are like some more structures like slow solar wind and slow solar wind with some magnetic signatures. So you will understand when I show the in situ plot. So then I implemented the a clustering technique developed by a PhD student from KU Leuven, whose name is Francesco. So it is the paper which was published last year. So I implemented the clustering technique to compare my results with this technique. So this is my in situ plot. It is usually like a 15 days plot. And okay, I will finish. Yeah, no problem. And this is the each represent different color represent the different structures in the solar wind, and this is the clustering result. So the pink and the highlighted area is the slow solar wind, which matches with my in situ plot. And these are like different timestamps in that year where I have like very only slow solar wind without any ICMEs or fast solar wind. So I took this interval and I compiled all the different structures like alphanic slow wind and magnetic signature and slow solar wind. Then I made a distribution, and I with the parameters like flow speed, density, magnetic field, and temperature. Then I saw this region has a very definite characteristics such as low speed and high density. Then I want to backtrack where it is coming from the sun. Then I this is the timestamp which it correspond the part correspond to in the in situ data. It's on December. So I took this 1 day data and I used the ballistic mapping technique, and which has a back mapping technique which consists of ballistic mapping and magnetic mapping. So it shows me the results from so I know the timestamp and velocity at 1 AU, so I can backtrack them based on constant velocity. And then using the IRAP connectivity tool, I can backtrack from 2.5 solar radius to the sun. So it points out to the active region, and there is a coronal like a
Vasant, can you finish in 1 minute?
yeah, sure. Yeah. And this is the conclusion which I conclude from my study. So these large-scale coronal structures observed in different UV images are very dynamic, and they exist for a very long duration, like several months. And the physical parameters and the statistical study shows that they can be clustered in different groups with different characters. And based on the in situ study, so there are like timestamps where I have like slow solar wind embedded between CMEs and fast solar wind, but there are like few timestamps that are very good with only completely very slow solar wind that can be used for the backtracking study, uh, because it has no perturbations like coronal mass ejection and fast solar wind. And the plot distribution of the in situ parameters shows that there are like different substructures in the in situ slow solar wind timestamp itself, and they can be studied further detail. And there for the December part of the slow solar wind, there is a part in that
Thank you, Vasant. I think we have to move on.
yeah,
So
sure.
sorry,
Yeah, it's fine,
we
no
don't
problem.
have question for time, so we will go for the last talk, and
Okay.
which is from Anmol. Anmol, can you share your screen?
Yeah, just
And
a minute.
Anmol will be presenting the magneto-hydrodynamic wave modeling in the solar wind and their observation with METIS. Yeah.
You see my
So
screen?
Anmol, yeah, go ahead whenever you are ready.
Yeah, sure. So hello everyone, good morning. I'm Anmol Kumar from the University of St. Andrews. I'm a final year PhD student right now, and today I'll be discussing some MHD wave modeling that we have been doing based on some recent observations with METIS. So there were some recent observations of waves in a helmet streamer. So by Vincenzo Amrita in this paper published last year. So what they found out in this paper was that they identified some bright regions in the solar atmosphere using white light coronagraphic images on board the solar orbiter. So these regions are such as, for example, region B here is a helmet streamer, whereas region C here is a pseudo streamer. So basically, when they process the data, they managed to get some. So they basically managed to get some time distance maps, and they were able to see some propagating features in these time distance maps. So these were like intensity fluctuations, but they have been interpreted as propagating density fluctuations in the middle corona. So they have found out these structures to be ubiquitous across all kind of structures, for example, pseudo streamers and helmet streamers, both, and with their propagation speeds ranging in between like 150 kilometers per second to 450 kilometers per second, and the mean height of approximately 2.5 solar radii or so. So when we got this data, when we got these results, we wanted to have a MHD modeling in order to explain these. And the two main questions that we wanted to answer was that what can MHD modeling tell about these waves, as in what is the origin of these density fluctuations, and what role do these play in coronal heating or solar wind dynamics. So for this talk, I'll be focusing on the first question, which is what can MHD modeling can tell us about these density fluctuations. So for this, we basically set up some MSD waves in a helmet streamer. So these are the equations that we are concerned with, and we are considering spherical geometry, gravitational stratification, thermal conduction, radiative cooling, background heating, and a uniform resistivity. We do our simulations in Pluto. So basically, this is the initial state of our simulation. For example, these are 4 different parameters. We start with a dipole and a Parker solar wind solution, and we just let this setup relax into a nice and smooth plasma profile that basically gives us an equilibrium state to set up our waves. So as you can see, as time progresses, it evolves into a steady state, which does not evolve too much in time, so that we can put in our waves. So you might have noticed that we have a source term in the momentum equation, which basically is for wave driving. So there's basically the product of two Gaussians, so as to localize them in space, and times a sinusoidal term to generate the waves. So we do this locally, just at the interface between open and closed field regions, because we wanted to track where all this where all the waves and the density fluctuations due to them can actually propagate. uh, sorry, can propagate throughout the domain. So we inject these in this location, and we can consider actually two kinds of wave drivers. The first one would be a magnetoacoustic wave driver. So these simulations are in 2D, so in the r theta plane. So we can consider a magnetoacoustic driver in which we drive the theta direction. That would naturally cause compressions because of the fast and slow mode waves, which are naturally compressive. And the other way we can drive the density fluctuations is by having alpha waves, but having nonlinear alpha waves, so that we can expect phenomena such as phase mixing or quantum forces that can basically mode convert the alpha waves into fast and slow modes, and that can basically generate the density fluctuations. So for this talk, I'm focusing on the alpha waves due to shortage of time, and I'll briefly mention how alpha wave mode conversion works via the action of quantum forces. So, for example, if you just consider the momentum equation, and the source term is aligned to the phi direction, which is the invariant direction for our simulation. So it re-enters the momentum equation in by having an additional magnetic pressure term over this over here as such. So the point motive force is basically the release of this excess magnetic pressure. So this is the B perpendicular component is a B phi component, which has been driven due to the alpha waves. So what it does is that basically I've shown you through 1D simulation. So basically here's an alphanic pulse, and this is a nonlinear alphanic pulse. If you just let it relax, what it'll do is just basically separate, and it'll also generate small density fluctuations that will propagate along with the alpha pulse. So this is also true in 2D, but what is important to note here is that because we have a very inhomogeneous media that has varying plasma beta, so there will be effects due to them as well. For example, if you have a low plasma beta, then the density fluctuations would be higher. If the plasma beta increases, the density fluctuations would be lower. So this is one of the things to keep in mind as I explain my simulation results. And the other thing to note is that if you note that one 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 velocity pulse over here basically contains two density fluctuations, basically a full sinusoid of the density fluctuations, which basically doubles the frequency, and this is basically because of the square term over here. So that is one important aspect to keep in mind when we deal about quantum forces. So here's the first simulation that we have done. Again, just to remind you, this is the region that we are driving our waves, a very localized region. And on the three panels over here, I'm showing the density. I'm showing the alpha waves over here, the reflected component of the alpha waves, and this is the density fluctuation that will be produced and which we are interested in. So what you'll see is that here we are driving the alpha waves. They would basically propagate along the loop and along the open field region. But as soon as they encounter the density fluctuation, as they encounter the um, high plasma beta region of the streamer cusp, the alpha wave signature just goes away, which is because the magnetic field just vanishes in this region. Not exactly vanishes, but yeah, goes to very small values, which means that the waves become numerically unresolvable. And what you can see on this panel over here is the density fluctuations. These are due to the fast and slow magnetoacoustic waves. So what happens is that these alpha waves, these nonlinear alpha waves, actually mode convert into fast and slow alpha waves, fast and slow magnetoacoustic waves, and they can actually propagate with them. Because the fast and slow magnetic acoustic waves are not necessarily tied to the magnetic field or to the magnetic field strength, the propagation becomes isotropic in the high plasma beta regime, and despite not having any alpha waves in this region, we do have a lot of density fluctuations in this region over here as well. So the last thing that we do here is, I'll just skip this slide for a moment. This basically shows the fast and slow wave decomposition. The left panel here is the parallel velocity, the slow wave component, and the fast wave component on the right. I'll just skip this for the time being, due to shortage of time. And then the next thing what we do is to basically consider slits, like what the Metis team had done. So I'll just show you one example of an equatorial slit that passes through the equator, and we are sampling the density fluctuations as well as the Alfvén waves in this region. So here are the time distance plots that we get. X-axis is the time, and the y-axis will be the distance along the slit. So here's the Alfvén wave, and what I'd shown previously in a video, there's basically a loss of Alfvén wave signature beyond this point because the magnetic field strength drops to really small values, which means that the waves either become numerically unresolvable or they have dissipated due to formation of small length scales. And the these are density fluctuations, and these are the line of sight integrated density fluctuations. So note that there's a 2D simulation, and to create the line of sight integrated profiles, we have just rotated the simulation plane about the north-south axis. But what is important to note is that these are not the actual propagation speed; these are apparent propagation speeds because waves and density fluctuations tend to follow the magnetic field lines, and this slit may or may not be completely aligned with the magnetic field lines. So this is what we have got, and there's basically a good match between our simulated apparent propagation speeds and the propagation speeds that have been observed by the Metis coronagraph. So I'm just considering one more case of magnetoacoustic driver, which is on the right, and to compare with the Alfvén wave driver, which is on the left, which basically shows the similar behavior. And finally, here are some more plots that basically show the similarity between these two. I'll just finish in a minute. Um, so so these are two more time distance plots. For example, the slit 2, for example, here is placed along one of the magnetic field lines and basically captures the slow waves and basically shows a good correspondence between for both the magnetoacoustic driver and the Alfvén wave driver with the slow speed that we were expecting. And slit 3 across the equator shows fast propagation speed just because the waves necessarily arrive perpendicular to the slits. Which again is basically similar for Alfvén waves as well as magnetoacoustic waves that we are driven. So finally, these are my conclusions. So the density fluctuations generated by observed by the Metis coronagraph could be generated either by magnetoacoustic waves directly or indirectly by a mode conversion of Alfvén waves. But because Alfvén waves usually go through a mode conversion, there's basically a doubled periodicity, doubled frequency associated with them because of the presence of the square term that I showed. And finally, the qualitative behavior of both the drivers basically is the same. Of the density fluctuation with both the drivers is basically the same. And we are also doing subsequent work on modeling of the pseudo-streamers, which again shows basically the same behavior. So I think that's it from my end.
Sorry, I'm muted. Yeah.
Yeah.
So thank you, Anmol. For if anybody have any question, please feel free to open your mic and ask a question. Meanwhile, I have a question for Anmol that you use Pondermotive force in your models, I guess.
Yep.
And I read some time back from the Laming, he tries to explain the FIP effect using these Pondermotive forces. So have you tried to predict any kind of elemental abundance using these Pondermotive force in your model, or it's just for
No.
waves?
It's just for waves that we have been doing, and honestly, I'm not aware of any FIP bias or anything of that sort due to
Okay.
quantum effects.
Yeah. Okay. Thank you. So if we don't have any questions, we can go for the end of the session. Thank you all of speaker. We can start the session summary, and if there are some few questions which are unanswered in the chat, we can discuss those. So I think let me check if which questions are unanswered. Thank you, Pratik, for highlighting these. Or maybe you can start, Pratik. Meanwhile, I will start looking at the question. You can ask the question.
Yeah, sure. I'll take that liberty for
Mhm.
asking the first question. Like many speakers have been talking about the Alphen waves or the study of alphenicity of the solar wind or CME. I was just curious that none of the speakers showed any error bar. We know that in the even in the in situ observations, they are not perfect. There are some uncertainties. Most of the time, ACE wind discover they don't match exactly, especially the density. So, like, how reliable are these studies, or is there a way to put error bar to showcase that okay, this much of probability or uncertainty is there in the conclusion?
So I think this question should be most related to Komal because he was, I think you or somebody else was focusing on very low densities to calculate the subalphonic region at 1 AU. Those densities were around zero point 0.1 particle per centimeter cube. So those
Can
were
you
very low. Yeah.
can you repeat the question? Sorry, I
So
couldn't hear.
Pratik, I think, can you repeat the question?
Yeah, the question is very simple. Since full observations are being used, the in situ observations, but there is no error bar. There should be error bar. There should be some uncertainties, right? And the final conclusion will depend on the extent of uncertainty. So, is there a way
Okay.
to incorporate that in the study?
Okay, in case of the polytropic index, if you are asking, so in that case, mostly studies go in a way that we take a slope errors, we take a slope of the density and that. So the error bar will go when you take a large amount of data and we check the spread of it. Here we do windowing process because see the data is very in a large amount, so very much so it's a huge data, you cannot do the direct calculation, so
So,
when we do it direct
sorry to
calculation.
interrupt. Sorry to
Yeah,
interrupt. I think Pratik meant by the error in the observation, like density, temperature, or velocity.
okay.
So we have error in
Yeah.
on those also. So I think he's not talking about the error in slope. So let's say if you are having a subalphonic region and your density is zero point 0.1 particle
Mhm.
and your
Mhm.
error bar is zero point 0.2,
Yeah,
then how sure
exactly.
you are that this density is reliable or not?
Okay, okay, that is not yet considered, like even I have not
Okay.
seen it, so yeah, good point, we'll think about it.
Okay. So same if we consider the magnetic field uncertainty. So anybody who has used the in situ data can tell us about that, what kind of uncertainty there are in the magnetic field.
Maybe I can chip in.
Yeah.
So when we use the in situ data, like I use PSP data, so that data is already level 2 and onwards.
Mhm.
And usually in the processing, since it is a very dense time series, they actually correct for the nearby, like photon noise kind of observations. So uh, I have not seen anybody use error bars in the time series of magnetic field or velocity observed in situ on PSP or solar orbiter.
Okay.
And that is primarily because of the processing done in the backend, is what I understand.
So for coming toward the PSP point, because I have used PSP data a lot. So if you go to span iron have a partial field of view problem, and that always have data problem. I have tried to fit, and I myself calculated sigmas by fitting the data, but I haven't calculated for magnetic field. But there are always some like standard deviation. I think we have for Aditya as well, and for all the spacecraft. I'm not that much aware of those deltas, but there may be some error bars. You can try and just check it if they are not making any problem to observation. And if Pratik, you want to add something that what these error can cause to the results, that will be
Yeah,
nice.
yeah. I always wonder that we know that there is some uncertainty, and there is always. But even if we are making very bold conclusion from the same in situ and without considering uncertainty, I think it's a red flag, and nobody is using. That's a bigger problem. That why everyone in the in situ community is not using it. And as Yogesh said that if the density is 0.1 and there is no error bar, it's dangerous to conclude anything from there.
I want to add further there means all of these L2 and L3 data product, they have these uncertainties given in their data product. So
Yes.
yes,
Yeah.
and another thing when we use the spacecraft, like for the spacecraft like PSP, they have flags whether the data is good quality. So if we are doing something like a statistical analysis, yes, we need to consider that. And we have observed that once we consider that data flag and the results are totally different. And yes, I was not aware of that. I should whether I need to use it for the one AU. I saw there these uncertainty over there, but we use specifically for the inner heliosphere spacecraft where it matter the most. And yes, it need to be appreciated.
Yeah, can I add a little bit more?
Mhm.
Yeah, please go ahead, Juby.
Yes, regarding two things, people talk about like magnetic field and density. The error bar associated with the magnetic field is very, very low. It's like a picotesla. So if you are looking like large scale structure evolution, then that doesn't care about like that fine scale, like picotesla kind of uncertainty. But if you are looking, for example, density or any bulk parameter, for example, density, temperature, or any flow velocity, then actually these are derived from the fitting of distribution function. So technically, what kind of there are multiple type of uncertainty? Well, like one come from the instrumentation itself, and second thing come from the what method you are using. Okay, so if you are talking about the methodology, then yes, if you are using, for example, just Maxwellian distribution function, then you will get around 10 to 20% uncertainty probably. But if you are using for bi-Maxwellian distribution to derive these moments, then maybe your uncertainty will be little bit low, and sometimes your distribution is very complex. So technically, what is happening is like if you take like wind, ACE, or solar orbiter, any spacecraft measurement like L2 data, the documentation clearly mentioned that, what method they have used and what is the uncertainty in the given parameter. Okay. Most of the time, if you're talking about SW instrument like electrostatic analyzer, then the proton has a like around 15 to 20% the error bar in the density, is flow speed as well as temperature in that range. But if you literally, but again, I said this will be very critical if you are looking for kinetic physics, where you literally talk about like what is happening at those micro scale. But if you want to understand, for example, dynamics, then I think that is not that much effective in your analysis. So it matter of fact like what kind of science you are answering, that will define like you should consider that uncertainty in your analysis or not, and what kind of physics questions you are asking to yourself.
Okay. Oh, thank you, Zubair, for adding this. So we have a few unanswered questions from the chat, and I think like for Sibotos, there was one question. For some wave numbers, was their alpha was more than 2. What does that infer? I don't know if you have answered it or not, but Sibotos, can you comment on that?
Is it for me?
Yeah, it was
So,
for you. For some wave numbers, their alpha was more than 2. What does that infer? I don't know. It
Yeah,
is
it was
related to.
Ritesh
no,
question.
I think
I
Okay.
think he's.
yeah, actually, what we have observed is, yeah, in some wave number there was alpha greater than 2, and we have to specifically see whether it is for uh, perpendicular cascade or parallel cascade, that is incompressible or compressible turbulence cascade, and based on that only we can interpret that. But generally what we did is we only focused on the magnetohydrodynamic scale, that is the fluid scale, and we didn't went into kinetic scales. So generally alpha greater than 2, it may seems it's a intermittency comes into the picture, means you have a lot more dissipative effects going inside into that. So it is my understanding. It may be wrong. You can suggest something else also. Means as far as
Thank
I
you.
understand, -2 features like that, it's more intermittency comes into the picture.
Okay, thank you. So Kishore is here, or
Yeah, I'm here.
Kishore is here. Yes.
yeah. So you have a question like, it is possible to connect the compressibility with non-alphanicity and relate in homogeneous nature of temperature inside magnetic clouds.
Yeah, means I think means we can connect the compressibility with the non-alphanicity, but because of which maybe the alphanicity gets reduced. But I'm not sure whether we can exactly connect it with the ICMA because as far as I know, the ICMA magnetic clouds are comparatively less compressible than the sheath region. But maybe we can connect it. But I will have to see.
Okay. So there is one more question. It is a general
Hmm.
query. What is the source of inward alphanic waves?
Yeah, so basically we have the two waves, right? Outward and inward. Usually we say that the outward waves are from the solar origin, that is, they are originated from the sun and they propagate in the interplanetary space. But whereas if you consider the inward waves, they have non-solar origin, that is, they may be formed by some kind of reflection or by some velocity shears, because of which, or maybe due to some wave-wave interaction. And if you consider the case of a CME, in the CME, you can say that suppose in one foot leg of the CME, the outward waves are propagating in one direction, let us say outward, away from the sun, whereas in the other foot leg, maybe they are coming back to the sun. So, in that sense, also you can visualize the inward waves within the ICMEs. I hope it is answering your question.
Yeah. Thank you. And I think there is one more question for Sneha. Could you please comment on interaction between ICME and switchbacks? Have you checked it? I think you answered it in the
Yes,
chat.
yes, yes. I
Okay,
have
okay,
not checked out that, but
okay,
we can do that together. Yeah.
okay. So then Vasant also answered the question. I think that was asked by Sneha regarding the uncertainties in the foot points. So that are all the questions. If you have any other question, please go ahead. Jubair, please go ahead.
Yeah, actually, I had a question for Sneha. I think I wrote in the chat, maybe she missed it. So the things like in the presentation, you mentioned that the alpha angle in the estimation of Z to define the switchback, you mentioned that alpha is the angle between the magnetic field and the theoretical Parker spiral direction, right?
Yes, yes.
Uh,
I actually
but
answered that in the chat as well. Uh, so,
okay,
uh, so the thing is, maybe you can just, it's collapse
yeah,
chat,
okay,
and
okay, okay.
so I can quickly summarize that.
Mhm.
What I meant by theoretical Parker spiral, it's correct that it should be a longer name. That so what we do is, because in situ data is spatio-temporally mixed, getting the background magnetic field information is very difficult. So first we assume a theoretical Parker spiral, and then using the observed in situ data, we basically calculate the background. And that's why we need the theoretical Parker spiral to calculate the background. And that's why the term should be background magnetic field calculated using theoretical Parker spiral. And the angle between the whole that and the
Mhm.
observed magnetic field will be the alpha.
Okay, but
Does that?
theoretical Parker solar, if you talk about theoretical estimation of the Parker spiral direction and the field line configuration, but itself depends upon many assumptions, right?
Yes.
So, and like you should have a quiet condition, very ideal kind of situation, and all those things. In that situation, you will either overestimate or underestimate your background magnetic field. So, how you will overcome with this one?
So that's why we only have instantaneous
Mhm.
magnetic field information at a given space and time. And
Mhm.
then the next information we have is at slightly different space and different time, and so on.
I
Mhm.
So
think you both can have some
yes,
Yeah.
personal
yes,
chat.
for
Sorry, and I think we can have last question from Pratik. And we already took 10 minutes from the
Yeah.
next
Yeah.
session.
Thanks,
And
Yogesh.
uh,
My
please.
question was for Vasant. Vasant, I saw it was really nice presentation. My only concern is that have you tried to quantify the projection effect when you relate the outflows using EUV images? Or have you tried to kind of do the fitting with global magnetic field extrapolation and some sense, any idea on that?
So for the outflows from the structures,
Yes.
I tried to do some height time maps for the flows from for the structures like streamers, and I didn't do it like properly for all the structures. It is difficult to do for high time maps for all the structures because they are existing for longer days, so I cannot do for like longer times. So for that only I did the in-situ one. So I know some timestamps like where there is like slow solar wind, like for 3 to 5 days, like those timestamps has like duration like that. So I can go back to the sun based on the backtracking and see what are the structures in the sun. So there I can do some high time maps, but initially I did some high time apps there. I see some flows, but not like very accurate flows, like not like very standard flows. Also for the global configuration of the magnetic field. So I tried the PFSS extrapolation for some large scale structures. Like I took like 4 transequatorial cusps, and I did the PFSS extrapolation, and it show these 4 structures exist for like several months, and they show that they switch the configuration. Two of them switches the configuration from pseudo streamer to helmet streamer or the vice versa, and some stays same throughout their observed duration. Yeah.
Yeah. Thank you, Vasant, and thank you, Prateek, and thank you all of the speakers, organizers. And if you have any other question, you can send an email to Indus or any of the organizer or me. We can forward your question to the speaker, or if you have an email of the speaker, you can always contact them. And I hope you enjoyed the session and the discussion. Thank you, and good night, the people who are in US, or good have a good day if you are in India. Thank you. Or maybe good morning for the people who are in Europe. Thank you. And I will hand over the session to the next session chair. I think Deepak Bhaiya is here. Yeah.
Yeah.
Okay. Okay, Deepak Bhaiya, over to you. And it's already 1:15 in the night, so I'm going to sleep. Good night.
Okay, good night.
Yeah, thank you.
Okay, welcome everyone. Now we will jump to the next, like the phase 2 of day 3. This is the session where we will be talking little different, because last couple of days and today this phase 1 we all the time were talking about the mostly solar interior and surface, solar atmosphere and some transient. This is the session where we will be talking how the solar like the sun is controlling, affecting the magnetospheric, ionospheric, thermospheric behavior. And this is so diversified. We have 5 speakers in this session. We will talk not only talk about the ionosphere, thermosphere of Earth, but also about Mars. So it is going to be more diversified presentations, 5 presentations. And I know the speakers now know that they have 12 minutes. Maybe if they can wrap up their presentations in 10 minutes, they will get 2 minutes to take immediate questions. And if there will be more questions, we will take to the end of, after all the 5 presentations will be over, then we will take all the questions. So without doing much delay, I would like to invite the first speaker of this session, who is Kalpesh Gag from University of Mumbai, and he will be talking about the universal time influence on storm time magnetosphere ionosphere coupling. So over to you, Kalpesh.
Sorry, so yeah. Is it visible? Yeah, thanks, Deepak Bhaiya, for the introduction. Yeah, uh, I'm presenting about the universal time influence on storm time, magnetosphere, ionosphere coupling. Uh, we are here. We tried to solve one simple question, right? If we have um, two storms with identical interplanetary drivers, and the both storms, if one storm hit at particular UT and another storm hits at another UT, whether the consequence on the geospace will be different. Yes, and we try to observe this through this work. And excuse me. Yeah. So for this, we use MAGE simulation, and as we know that the MAGE simulation, there are different models in a different regime. We have Gamera that solves that's for the outer magnetosphere. Then we have RCM, that is a Rice convection model, which is for the inner magnetosphere specifically, which try to simulate the ring current. Then we have a remix, which is a ionospheric solver, which solves MI coupling equation basically, and there is a TIGCM. So all this model is known to be as a GTR, that is Gamera, RCM, and a TIGCM. For this particular study, we use GR, means the difference between the GR and GTR is kind of for the GR, where the remix is being used. The conductance is empirical, where when we come up with the TIGCM, the conductance, that is ionospheric conductance, which is a physics based. So for this study, we specifically use GR configuration, and the reason was simple. For both GR and GTR, the results were qualitatively same, and for the further modification, GR was so simple, and that's why. And we use this, or typically choose this storm. The reason was also simple. Like you see this storm with a definite sheath there, shock there, and the magnetic cloud, not that like 2, 3, 4 ICMEs like May superstorm. This is a single ICME which results into the kind of the extreme storm about 400 nanotesla, minus 400 nanotesla CMAX. And yes, so our main result was the interhemispheric asymmetry. So let me explain what it is. Means there are some time series quantities or the integrated quantities. The first, which is phi, that is a potential. When we saw or when we see in ionosphere, there are the potential contours that results from the convection, and thus phi, it is measured as a maximum and a minimum, difference between the maximum and the minimum, and which is known to be as a CPCP, like cross polar cap potential. And here it is a time series of that CPCP, that is a phi. Then there is a FACs, integrated FACs. If you see the right side plot here, you will see the convection pattern right here, which is minus, and here it is positive. The FACs, that field line current, are shown in a color. For the red color, these are the upward field line current, where the electron is precipitating down, and where it is blue, which is a downward field line current, where the electrons are coming out. And these are the integrated quantities, the integrated current over the particular grid, and you will see here. And then it is EHP, the hemispheric power that comes with this electron precipitation, and the Joule heating, that is summation of sigma p, that is conductivity, Pedersen conductivity, and the electric field. And if you see here, for the particular time, these quantity are showing some differences. Like for the north hemisphere, these are elevated here. For the FECs, you see the southern hemisphere receiving more currents. EHP, that is electron precipitation, or the hemispheric power with electron precipitation, that's also more. Joule heating is also more. So this is known to be as an interhemispheric asymmetry that we observe. So whether means yes, we can observe this interhemispheric asymmetry in the geospace, and it is basically a seasonal, because as we know, during the equinox and solstice, our one of the pole just move towards sun, move away from the sun, and whether if the one of the pole is towards the sun, which will which will get a more solar illumination as compared to the other and will result the more quantities over there. So this is, but this specific storm was near October and we kind of the equinox where our dipole is more aligned. Still, we observe this interhemispheric asymmetry, and then we went for the what causes this interhemispheric asymmetry. Then we did some controlled simulation, and that's kind of advantage of this simulation where you can control few parameters, and we control these parameters. Like we know about these different drivers for the interhemispheric asymmetry, like a by. I'm a by, then the strength, then this particular storm, if you see the vz was more, then we typically shut down all these parameters, ran the simulation again, and we saw these changes. But most of the time this asymmetry was still there. But there was one case where we use a constant conductance in the both of the hemisphere, and then we found that yes, the asymmetry was not there, everything was symmetric. So what we observe here, the basic like the conductivity was, or the conductance in the both of the hemisphere, the differences was the driver for this interhemispheric asymmetry, but how it takes a role in the equinox. So then we come up with this, like we know that the rotational axis, but there is also a magnetic axis, and there is typically the offset between the rotational pole and the magnetic pole. And as our Earth rotates, this magnetic axis and magnetic pole wobbles around our rotational axis with the dipole tilt, and where at that magnetic axis is there, it can do the motion like towards sun and away from the sun. And if you see, this kind of storm was so special where the dipole tilt means where the southern pole was just going toward the sun, the large step in BZ has occurred, and when that occurred, you see the asymmetry had started, and when the dipole tilt means like the geospace is again coming with that original period after the 12 hours, we see that asymmetry has been vanished. Then we did another kind of controlled experiment where we shifted our interplanetary conditions or the geospace condition by 12 hours, and it is called as a UT shifted experiment. And in the UT shifted experiment, we shift everything by 12 hours, and then we observe that yes, the asymmetry also has been shifted by the 12 hours just before the storm. So how was the things like if we see the geographic pole and rotational pole motion over here, when the storm happens and when there is a large step in BZ that was around 20 UT, the south pole was just turning towards the sun, and when we see here, and the north pole was there, and that was the difference in their conductivity. And if you see that both the UT shifted case and the original case, you observed all these things here. The asymmetry has been shifted earlier when the simulation with run had been ran with the UT shifted cases. But one of the interesting fact here we observed, typically if you see that there is a difference in the phi here, the means like a potential. Generally in a geospace, this phi, that is a CPCP or the potential, it is observed that it is kind of the proxy of the day side reconnection, and once the day side reconnection happening, people observe and people kind of assume that yes, these reconnection which drives the power in the ionosphere from the day side reconnection, it should be symmetric. But here we observe the CPCP, the potential, to be asymmetric. Then we observe that there is something different. Means if you see here, this is a polar plot over there. You see the convection contour over there. You see the field line current, and you see some dark line over here, which is OCB, that is the open close boundary. The region, the field lines typically inside these particular that black line are near to, are the open field line, and out of that are the closed field line, and this the region around that open OCB, we called it as a polar cap, and we observe that the one of the potential counter is closing inside that particular open area. In general case, what we observe, these things means if you see in this here, the potential counter that just lie on the ACB boundary, but here we observe that this potential counter has been closed inside the open area, and we identify that this is total because of the lobe cell convection, and that lobe cell convection was due to the combination of BY and the tilt effect. So yes, the day side reconnection is also there important, but when we are talking about the complete MI coupling, the lobe cell reconnection is also taking place over there, and that has contribution in a the convection. And when we go there and we then simulated the auroral indices, that is a synthetic indices for the both of the runs, like for the UT shifted and for the original run, and then we observe that when the storm has been is UT shifted, there is increase in the eastward electrojet, specifically when you see the plot at the right. And why is it due to? Because the precipitation has also changed. The hall here, if you see here the hall conductance, and the hall conductance has been plotted here, and you see for the original storm at a particular time step. And so sorry, the time step had been cropped out here, but at 235 UT you observed here at the original case, and at UT shifted case, these the conductance and the precipitation was quite different. So this means that when the storm the UT is changed, the internal state of the geospace is different. Yes, we observe the difference. And yes, the overall thing, like the UT matters, the UV effect at the equinox, like the diagonal variation in a dipole tilt, that just drives this inter-hemispheric asymmetry, and that matters. And we did another experiment where we observed that the indices like SMR indices, which is close to the DST and the CMAX, when the storm is UT shifted, it reached the peak just, I think, 4 to 5 hours before than the original. So this also we haven't get a detailed idea about it, but yes, these are our few results. And further study will elaborate all these things with the DST and the other geospace quantity. And yes, the moral of the story, UT matters. So yes, thank you. I'm open for your question.
Thank you, Kalpesh, for this presentation. I do see there is a question in the chat box. Can you read that question? And
Yeah, hi Kalpesh, it was a nice talk. I
Yes,
just
yes,
wanted
yes,
to
yes.
know how you calculate the hemispheric power. Is that just like voltage into field align current?
No. This is not
Then,
voltage into field align current. This is specifically with the E flux into the number flux that is coming inside the ionosphere with the electron precipitation. That's why I specifically mentioned this is not total HP hemispheric power. This is coming with only electron precipitation, which means the energy flux into the number flux by the electron.
okay, thank you.
Kalpesh, I have like a couple of questions. That
Yes.
auroral electrojet, what is the physical significance of that term? You showed just in the previous slide, yeah. What does
Yeah.
that
So
like? What does that signify? What is that quantity, and what is the physical interpretation of this? So what?
the auroral electrojet, specifically the eastward electrojet that we observed here, the substorm indices, that is SMU and SML. So typically they are due to due to the Hall current specifically, and when electrons precipitate, then you see here the eastward electrojet. They specifically were observed here at the dust side of here. So when as in the these are the typically substorm indices. There is a westward electrojet as well, there is the eastward electrojet as well, and these are helpful in the current closure, specifically in ionosphere when the field and currents are coming and the substorm is happening. So these are typically observed in the ground magnetometer near the polar region where the supermag indices are there, and typically the change in the magnetic field perturbation that we observe here, and they are measured measured with the nanotesla. And you see there, like generally in a substorm cases, when the westward electrojet is observed to be westward electrojet, like the SML, when it observed to be increased, we called yes the substorm there. Then we defined the phases of the substorm, like growth phase, main phase, and the recovery phase. But here, what we observe that the eastward electrojet here, and that eastward electrojet been affected by the UT, means UT changes, means when we change the UT. And this is typically because the conductance, or the conductance, specifically the Hall conductance in a UT shifted case, that been increased in that case, and that reflects in the eastward electrojet specifically.
I see. Okay. Yeah, it is good to know that. Like, whenever any geomagnetic storm happens in the research community, when we are looking at its impact on the equatorial or low latitude ionosphere, generally what the researchers do, they look at the IMF BG component, IMF BY component, or the solar wind, all these measurements at L1 point.
Yeah.
And also we look at the auroral, like some magnetometer measurements over the pole to understand how much energy is getting precipitated to the pole. And of course we assume many a times, like personally also myself, I assume it is happening in the real time.
Yeah.
And the another assumption goes there is that at the L1, those observations that are available, those are corrected to the earth's, like in the real time.
Bow shock, yeah, they are connected to the bow shock, yeah.
Okay, so but still from the Bosock to the, like the particles come to the Earth's ionosphere, like the auroral, to create the auroral electrojet, there is a time lag,
Yeah.
right? So
Uh,
your title, when you said the UT time matters,
yeah.
at first I was thinking probably you are talking about that difference in the UT time.
No, my UT time matters
Right,
mean at what time typically the storm has been hitted there in a magnetosphere, or typically in a geospace. That
right,
matters. Means specifically if a storm certainly means if a busy step has been observed at particularly 20 UT, and there is another storm with the same identical all these interplanetary condition, and that occurs at I think around 2 UT in the morning,
okay.
these two storms will be different, because as we know the external things have been important, but the internal state of the geospace, that's also matters when we talk about its storms and SMI, that is solar wind magnetosphere ionosphere couple.
Right. Yeah, I want to add one point here, which you may be interested. Like in 2024, that major super storm that happened, and recently in 2026, January 10th, there was another superstorm. In
Yeah.
the ionosphere, we see completely opposite impact of these two
Yeah.
storms.
Yeah.
In one case, the change in the IMF BG, if you look at the IMF
Yeah.
BG or IMF BY, they show a clearly different pattern in these two superstorms. And as a result, on the ionosphere, we are seeing a completely different effect. So now the
Yeah.
question in the ionosphere, like like people who are doing early career, who are doing ionospheric research, we just take those IMF BG, IMF BY, those variations just as like input, but we really don't understand why those happened. So in that context, like here, the people who are sitting here, they know better why those things happened. So is there any kind of investigations or study that is happening to understand those difference in the solar wind conditions? If anyone from
Uh,
the audience, if they can answer, or Kalpesh, if you have any idea about that.
uh, Generally, I have the another slide, so I just miss that. I just keep that slide away because I saw a lot of initially people were running out of the time, and that's why. So generally, when we talk about the geospace and all these things, generally we know the Dungy cycle and how it occurs. We know that busy reconnection over there. The things had been dragged, the convection that goes in the night side, then again the night side reconnection, particle being transported towards the sun to the like bursty bulk flow and then the feeder line current and everything just happened. But the IMF topology has been important here specifically when we are just taking the southward condition over there, we may observe this kind of things over there, which has been shown here on the right side, the convection. Though the real time, this is like the in ideal case, this is also different when we talk about the gradient in the conductance over there. This is so ideal case.
Okay.
In the real case, it's quite different. But when we talk about the BY reconnection, the BY reconnection that comes with the different topology, where not only the north-south, now the dawn and dusk. I saw the Shirsha is also here, and he has a recent work with that I am a BY kind of things like there. So in the BY case, like the things been different where the dawn dusk asymmetry also takes place over there, and that dawn dusk asymmetry been changed, and that also changes the ionospheric convection pattern over there. And another thing, as we know, IMA, BY, and BZ are important, but the IMA BX that also matters a lot. When we talk but generally when we are doing some geospace or the simulation, that simulation, the BX quantity have been neglected initially because when the BX is there, it can cause an extra monopole there in the simulation, and that's why to just reduce all this thing, we just neglect the BY, but BX. But the BX also matter because it adds the component in the solar direction and it just shifts the reconnection from the solar subsolar point. And I think the recent advancements are people are taking in that direction also. And that what I know about the IMF cases, that IMF BX, BY, and BZ.
Okay. Yeah. No, that is clear now. Okay. I don't see any more questions in the chat box as of now. So let us thank Kolpes. And Kolpes, be there. We will take
Yes.
more questions towards the end of the session.
Yeah.
So I
Thank you.
have got a notice from the organizers that three speakers are not present at the moment. So we'll go directly to Alwyn Roy. I think you are there, Alwyn.
Yes.
Yeah.
Give me a
So
moment to present the screen.
yeah, he is from GFG Helmholtz Center for Geoscience from Potsdam, Germany. He will be talking a different aspect of magnetosphere where the topic is developing analytical chorus wave models using the data from Van Allen probes and array satellites. So, Alvin, you can start. Yeah.
Am I audible and is my screen visible?
Yes, you are audible and we can see your presentation.
Okay.
Perfect.
Okay. Hi everyone. Myself Alvin Roy, a PhD student under the supervision of Dr. Didong Wang from GFC Helmholtz Center for Geosciences, Potsdam, Germany. Today, I would like to discuss about our recently developed chorus wave model using the statistics from Van Allen probes and Arase satellite. Before I proceed, I would like to express my sincere gratitude to the organization team of ISHA 2026 for organizing such a nice event and also for giving me an opportunity to present this work. As we are from different domains, I would like to start from the solar wind. When the solar wind interacts with Earth's magnetosphere, it transfers particle and energy to the inner magnetosphere. When we talk about inner magnetosphere, we are specifically talking about this region close to Earth, which we call Van Allen radiation belt, which is a region with high energy particles. Due to this particle injection, anisotropy is generated, which in turn generates some plasma waves. And this plasma waves then interacts with the particle in this radiation belt, driving different kind of space weather phenomenon. Among these different kind of plasma waves, one of the important wave is called chorus wave, which is a naturally occurring two-band electromagnetic wave which appears in low-density regions. Why it is important? Chorus wave can both accelerate electrons, which can then cause threat to our space and terrestrial assets, and also scatter electrons, which causes diffuse aurora and change in atmospheric chemistry. I would like to draw your attention to the x-axis of the spectrogram. In our study, we always define our spatial parameters based on MLAT, which is magnetic latitude, MLT, which is magnetic local time, and then L shell, which is a radial distance which is normalized to Earth radii with the assumption of dipole. As we have briefly seen the importance of chorus wave and their effect on space weather and our space and terrestrial assets, it is evident that we need to know more about chorus waves. As chorus wave is a global phenomenon, statistics from a single satellite is not enough to get a comprehensive spatial and temporal coverage. Furthermore, we need a simple but very robust model so that we can incorporate them into our space weather nowcasting and forecasting systems. Through this study, we are trying to address the gap of the present existing models, such as the limited coverage, spatial discontinuity, and excessive complexity. In our study, we are using the statistics from both 1LN probe A and B, which is also called RBSP, which spans over 8 years, but the data is limited to 20-degree magnetic latitude. So we also introduced an 8-year statistics from Arase satellite, where the data is extending up to 40-degree magnetic latitude. And these are the data sets which we use from both the satellites. Now comes the key question. Does these two data sets agree with each other? To address this question, we found a close conjunction where the satellites were within a distance of 900 to 2000 kilometers apart with clear upper band chorus signatures. You see a difference in the spectrogram, which is mainly due to the fact that the cadence of RBSP is 6 seconds, whereas for Arase it is 1 second. And also we see a rising trend in the frequency for RBSP, whereas for Arase it is falling trend. This is due to the fact that the satellites are in the opposite trajectories. We try to find a point-wise correlation which appear to be weak, which is actually expected as the coherent scale of chorus waves is between 300 and 700 kilometers, which is far below the lowest separation between these satellites. So instead of points comparisons, we looked at the distribution. On the left side, we are seeing the probability density function of both Arase in the blue color and RBSP in the orange color. We can see the distributions, the means and the medians are agreeing with each other very well, which gives us confidence to combine these two data sets without much cross-calibration efforts. Now let's go to the modeling setup. We are closely following the Wang et al. 2019 methodology, where we separate the spatial parameter and the geomagnetic parameter for the model. For spatial parameter, as I mentioned earlier, we are considering MLT, L, and magnetic latitude, which gives a basic magnetic intensity, and then it is scaled according to the geomagnetic condition, which is driven by Kp. The spatial parameter is a second order fit of these parameters to the root mean square magnetic intensity of chorus waves, whereas the scaling parameter is a fourth order fitting of Kp to the RMS BW. For those who are not familiar with Kp, it is a 3-hour geomagnetic index which is maintained by my institute GFC, and we also have nowcast and forecast products for Kp. And we also provide different state-of-the-art solar space physics and space weather products, which can be seen at spaceweather.gfc.de. Before moving to the results, I would like to show our statistics. Here we are seeing the sampling time where all the x-axes are Kp and the y-axes are from left to right MLT, L and magnetic latitude. Here we can clearly see when the Kp goes above 6 plus, the data is comparatively sparse, so we limit our model within Kp 6 plus. Here again we are seeing the sampling time, but for the spatial parameters where each subplot is shown for different MLT sectors. Here we can see as the magnetic latitude is low, we have higher number of samples relatively. It is due to the fact that we have statistics from both Arase, RBSP-A and RBSP-B, whereas in the high latitude the statistics is completely coming from Arase only. Now moving towards the result, here we are showing the scaling function for upper band chorus. The first panel shows the sampling time of each KP value, and the second panel shows our KP BW model, and the third panel shows our scaling function. In the panel B, the blue dots are the actual data points and the black solid line is our model, and the scaling factor is derived by dividing this model with the averaged model for entire KP region. This is the same figure but for lower band chorus. For both upper and lower band, we can see our model is closely following the data, thus giving a much more confidence to our scaling factors. Now moving to the spatial parameters, on the left side we are seeing the observation and on the right side we are seeing our model. I'm only displaying a particular MLT sector where the chorus wave is much active. One might be asking, like, the whole point was to extend the spatial coverage, but we are only going up to 10-degree magnetic latitude. It is because of the fact that the upper band chorus is limited to lower latitudes, whereas the lower band extends up to higher latitude, as you see here. Again, here left side is observation and right side is our model results. For both models, we have high R square values, as you see, and which again increases our confidence to use these models to drive our space weather nowcasting forecasting systems. Now coming to the summary, we developed a chorus wave model for both upper band and lower band using the statistics from RBSP-A, B and ARAS-A satellites. Our lower band model extends up to 40-degree magnetic latitude without any spatial discontinuity. Furthermore, we created a KP-dependent scaling function in a global aspect, which can not only scale the magnetic intensity of chorus wave, but also the diffusion coefficients thus calculated, which increases our computational capability. As the next step, we would like to analyze the effect of chorus wave, particularly at higher magnetic latitude, by calculating the diffusion coefficient and implementing them into different radiation belt simulation models. That's all from me. Thank you for your attention, and I'm open to questions.
Thanks, Elvin, for this nice presentation. So if anyone has any questions, you can raise your hand.
May I ask? May I ask?
Yeah.
Uh, Hi, Arvind. Thanks for the talk. Yes, this means you are parameterizing these wave parameters using the geomagnetic indices. Am I right in a short form? And you are using the KP.
Yes.
Yeah. So yeah, what about the other indices, that is AL, AU, and all? They are also to be important, right? But
Yes, the main focus of using KP is the fact that most of, like, not all, but many of the radiation belt forecasting nowcasting system can be driven by KP. So it is more accessible when we use KP, fact number one. And fact number two, if we use the indexes like AE or AL, which is highly variable in terms of the values we get, like it is 1 minute cadence, for example, and also the value varies very rapidly, which might be also, couldn't give the exact a stable conditions for the modeling processes. Since we are using a statistical model, we can further do it better with AE, and we also tried that. And yes, the model which is driven by AE can perform better than KP, that's true. But when we think about a global aspect where we want to incorporate this thing into different other systems, as it is not a standalone thing, it needs to be incorporated. We need to think about the driving factors which can be incorporated into multiple simulation systems. So that's why we prefer KP. And one another option is to use HP, which is similar to KP but with a 30-minute cadence, and which don't have a cap at the value 9. The KP is limited between 0 and 9, whereas HP is open-ended. So we can drive the same model. Our system is flexible enough, and we have also tried them. We have tried them with AE star, HP30, KP, and etc. Like we can drive our model with any geomagnetic driving parameters.
Thank you.
Did I answer your question?
Yeah, so in line to what he asked, you mentioned that you used HP30 also, right? So that is a
Yes.
high cadence data, I think.
Yes.
So did you find any like drastic difference in your modeling results, or is just the same?
When we look the models with HP30 and KP, we find that in general they follow the same trend, because
Yes.
the main differences which we see in this sector is like, for example, when KP is 6, the HP30 might be 6 minus. But
Yeah.
in our model, we consider 6 minus 6 and 6 plus as 6. So there are minor differences, yes, but if you look at like a long term, the differences are comparatively minor. But we need to actually implement them into radiation belt simulations to see exactly how much this difference matters. But if you just look at the magnetic intensity in a very uh, rough estimates, it seems almost similar. But AE drives it thing a little bit different. That's correct.
Okay. Thanks.
Alvin, can you show us your slide too? I have
Slide
was
two.
yeah, where you are showing that Van Allen radiation belt. That
This one?
no, maybe the next one. Yeah.
Sorry. This one or this one?
No, no. You had a cartoon of Van Allen radiation belt, and you are showing. You mentioned.
This one?
Yes, this one.
Okay.
And the chorus waves that you are looking here is in the like low electron density region. Is that what
Yes.
you mentioned here?
Yes. So the waves, we have different waves, and these waves are parameterized based on their frequency ranges and where they appear. So the chorus wave is generated in low electron density region. That means outside the plasma sphere. So
Right.
inside plasma sphere, we have different waves called His waves. The classification of waves, we also look at the fine structures, but in a broader sense, if we are speaking, the classification is based on their frequency region and also where they appear. So
Okay.
the chorus wave is specifically appearing outside the outside plasma pose, which is the boundary of plasma sphere. That means low density region.
Right. Okay. So, how well do like current analytical model they capture this the effect of the extreme solar conditions on this?
The solar conditions are like taken from different indices as like KP or AE or HP or anything.
Yeah.
And as we talked in the last presentation, there could be a latency in these models, like I mean in this indices. Like for example, when you see a ULF wave spike in your spectrogram, but the HP or KP spike might be appearing 1 hour or 2 hour or 3 hour later.
Right. Yeah.
So that could be a problem. But if you are just looking at the indices rise and the effect of them in the in the modeled value of this chorus waves or any other waves, they are pretty similar. So if you can provide the accurate index at that particular geomagnetic condition, then almost all the statistical models will give you roughly a good approximation of intensity of these waves.
Okay. Okay, I see.
So it completely depends upon using which index you drive the model and
Right.
how you like, it's not like even in different radiation belt models, even if we have, for example, like it is driven by KP, some models may shift this KP like 1.5 hours before so that it can
Right.
locate
Yeah.
this KP in the middle position or something like that.
Okay.
And specifically depend what meant to be the geo effectiveness. When we talk about these indices, I mean generally there not every time these indices reflects the severity of the storm specifically. Means we can see some of the storm where it reaches a maximum DST. It might have moderate with the particle precipitation, but few of the storm where the DST is not been reached, but they are responsible to increase these particle population in radiation belts or at particular altitude. So it it depends what we called as a geoeffectiveness, either with the indices or with that particularly storm severity.
Okay. Yeah, Dr. Mohinder Arori, you have a question. If you can unmute yourself and ask the question to Alvin.
Yeah, Alvin, right, nice talk. So, what are the data sources to study the inner as well as outer radiation belts concentration, like proton concentration?
Yes, so as you can see in this slide, we are getting the density from the in situ measurements from the satellite. So when the satellites move in the orbit, like in the apogee, perigee, they are constantly monitoring the electron density and that in this orbital path. So if we are just talking about in my study, we are only concerned about whether the density is high or low below a threshold. So we just take this electron density and then we see whether the density is below or high of this plasma post threshold. And if it is higher than the threshold, then that means it is inside plasma force. So just neglect that part. And if it is lesser, then that means it's outside the plasma pose. Then check for the frequency conditions. Does it match? If yes, then take it as chorus waves. Did I answer your question?
Yeah, these are available for open
Yes,
source?
yes. So RBSP, actually the mission ended in 2019. They give us a level 3 density data product, and Arasa, which is currently ongoing. They also give us a L3 plasma density, electron density product. So these are derived from certain observations. And furthermore, if you are particularly interested in particles, they also have this particle flux observations, which I don't deal with them, but they have those data products too. So here we are here in my study, I am only using the density number. But if you are more interested in the flux with energy resolution and all, they also have that products too.
So, can you share the link of the RBSP if possible?
Yes, I can. Maybe along with the chat, I will share in the chat later if that's okay with you, or if you can share me the email, then I can send you via email too.
Yeah, I'll share my email ID.
Okay.
Thank you.
Welcome.
Alvin, in your like future work, you projected that you will be doing something related to that calculating the diffusion coefficient.
Yes.
So one of the question which always stands like in this kind of like analytical chorus wave modeling, what is the biggest uncertainties like when we translate the observations into the diffusion coefficient?
So basically, in all statistical models, we are focusing on either averages or medians. So, if you look at the fine structures or like and most of the most of the simulations are assuming the things are quasi-linear. So if we assume things are quasi-linear, it is very simple and very easy to solve, like comparatively easy to solve. With this assumption, this averaging and this processing are okay. But if you need to know exactly the true thing, then we need to think about this non-linear processes where we need exact values rather than this averages. But when we speaking from the forecasting or nowcasting system, which is almost impossible. For example, if you need to predict like for 1 minute ahead for a non-linear process, it might take 1 hour. So we are not saying we are perfect, but we are giving a value which actually is similar or resembles the actual situation of actual situation of the radiation belt based on these models.
Okay.
So I think we are doing good in that sense. But if you
Right.
need exact physics, like everything exact to the point, then yes, we are lacking the capability of this non-linearity and everything. But in a general sense, these approaches are good to solve.
Yeah, no, I mean, the plots that you showed, definitely I agree with that. But I was curious when you mentioned that you are going in future, you are thinking of the translating to diffusion coefficient. I thought, okay.
Yes, because like all the simulations, as we see, we cannot directly implement everything into this simulation. So what we do is like, okay, this wave at this particular condition, it will, the effect of them on this particular particle population will be like this. That's the diffusion coefficients. So whenever this simulation runs, it look up in this table we created. And in that table, they say, okay, this given conditions, these are the scattering or these are the acceleration parameters. It takes the parameter, then runs the simulation. That's the whole concept of having this diffusion coefficient. And depending upon the which model we use, the value differs and the effect in the simulation changes. So that's the workflow. If that answers your question.
Yeah, no, I understand. All right. So is there any other question to Alwin? Probably I don't see any more questions. So let's thank Alwin for this nice presentation and taking these questions.
Thank you for your time.
So now there's, I mean, there are supposed to be 3 more speakers, but we don't have any more speakers. So I think now it is time for any discussion. If anyone wants to ask anything to both the speakers, and we can have some discussion. Just to start with, I mean, I think people have asked questions related to your presentation. So particularly my interest, since there are more solar physicists here among and the early carriers, so I think let us bring some questions where the magnetospheric and ionospheric community, they really depend upon the solar physicist. Like I mentioned after Kolpe's presentation that in the ionospheric and magnetospheric community, most of the time we use the solar indices kind of like as they are, without understanding much why the magnetic field are showing that kind of behavior. So it is a question, like you both can like reframe my question, but it is more to the solar physicist group here, that whenever a solar storm happens, we have the interplanetary electric field and magnetic field measurements at L1 point. Now, is there any kind of understanding for each storm in your community? Do you guys try to understand the nature of the IMF, BG or BY, like the solar wind conditions for each storm? Do you guys try to understand, or is there any kind of like a committee or something to whom we can approach if if we really don't understand why it is happening, or if some ionospheric early carrier really wants to understand that why the solar wind conditions are like this in this storm but it was not in the other storm, so whom we should approach?
Maybe I can start with that because I'm a part of a project which actually try to answer the same question. Um, So, we like in GFC in our section space physics and space weather, we have a cascaded forecasting system which takes the data from this L1 point and then predicts the solar wind, then it predicts this KP, then it predicts our radiation belt forecasting system. So which is both physics based and also machine learning based. So it's a mixture of different models which do all this process in sequence, which can also seen in the website which I said spaceweather.gfc.de. It's one of our flagship product, which is also being used by ISHA. So in this system, the thing is how we understand the physics at the L1 point, because when we observe something in L1 point, especially if we are talking about the particles, we have some time latency until it reaches this Earth's magnetosphere, and then how this interaction, and then there is another latency that is this interaction reflects in the polar caps, and then another latency it goes through the other observation magnetic observatories in the lower latitudes which measure KP and DST. and also the ring current. So we have the basic understanding of physics, but if we try to look into the observations, as in the first presentation said, we need to consider the timing of these observations. The timing is very much important, because even if you so in the project which we are dealing with, it talks about understanding the waves, their effects and all, but all of these things are driven by this geomagnetic condition, which is like an index, irrespective of what index it is. So it was a new knowledge for me to know that the UT, like if it appears on like 12 a.m. or 1 a.m., it also matters. For me, it was a new knowledge. So this kind of timing could address most of this issue, I guess. Timing is the important thing, because we need to, when we have an index, we need to look into different things. For example, I think from my understanding, most of the people, what they look is the VLF observations and they look when the VLF the spectrogram spikes, and does the index also spike at that point or not? And we see sometimes they are not matching. So when we manually match them, then we could do better simulations or predictions. I think that's
Actually, my question was in a different direction.
Oh, I'm
Like,
sorry.
yeah, no, it's okay. I understand. Like, your answer you gave in a, like, more like in the observation point of view in the Van Allen radiation belt. But my question is to interpret the solar wind conditions as a ionospheric early carrier, whom I know, like I have friends who are working in the solar physics, but I know that not all of them work in the similar. They can explain me why in this term the IMFBGs, the solar wind conditions, are behaving like this. In the other term, they are behaving differently. So from where I
Uh,
can get knowledge about those?
I will try to answer this question not from the like a solar perspective, but I can answer from the interplanetary perspective.
Right.
Yes, right. Means as a ionosphere and magnetosphere people, we bother about the IMF clock angle, like both BY and BZ, and the dynamic pressure. But it depends on the various factor. The one factor is where it has been measured. For example, like for the storms and like for the May storm, you might have observed that the storm, their people use their L1 input as for their models, and their models behave differently whether they are using the input from the wind, from the Omni, or from the Themis. This means that, like, as we are explaining or as we are uh, like assuming these large scale structure, there are small scale variation, like a spatial variation that also matter. It matters whether these ICME, whether they are coming like a single ICME, whether it is multiple ICME. As they are with multiple ICMEs, like Pratik is there, he might have a better idea about how these ICMEs, CMEs, they interact with each other. There are large topological changes in their, like they kink, they rotate, they deform, they compress. Everything happens there, and that processes just changes their topology when it comes at the one A. So it matters where, like at either there is a single CME, either, and it matters where either it is CME or it is a CIR or it is an interaction of both or their other structure. It matters where they are the tangential, it matters whether they are the equatorial, and a lot of things. But they are, yes, all these modeling efforts have been taken to understand their interaction and their propagation, whether they have been emerged from the solar surface and where they are propagating in an interplanetary space. So yeah, that's from my side.
So, Pratik, you have raised your hand. You want to say something?
Yeah. Maybe a brief comment on this, and I have a separate question. My comment will be that nobody can answer that question. We don't know when the BZ will be plus or minus. There is no way.
No,
The
not
existing
when
models.
it is going to happen. Why it happened last time?
Uh, I think the problem is in maybe the framing of the question. It's
Okay.
I think you are asking whether we can predict
Not
at what
predict.
time.
Can we explain in the
Yes,
previous
we can
storm?
explain from the solar wind MHT physics
Okay.
that because the magnetogram was like that, the global topology was like that in a specific sense, and hence the solar wind near the magnetosphere was like that.
Okay.
That can be explained, but through
Okay.
physics. But for if we go as case by case or sample by sample, it is extremely challenging because there are several things which we don't know or we don't have the initial conditions or the observations of that.
Okay.
So we have large amount of uncertainty in the prediction, even though we know the basic physics of that or bulk properties of that. But my question is slightly different that even we know the exact property, even if the CME is fully minus BZ, even if the DST is minus 400 nanotesla, what impact it will have in terms of space for those things? We have seen minus 400. We saw the aurora in Boulder, I think, which is rare. But I didn't read anywhere that there was satellite falling from the sky, something happened, or like any power grid failure. Nothing happened. So what does it tell you? Is it really impactful, or we are putting a hype over it that okay, CME has come, this is important, that is important. So what do you guys think about that?
Yeah, yes, that's what the question I raised initially. Geo-effectiveness, whether in the term of indices or the geo-effectiveness in the terms of their impact. Like this is quite means as you mentioned, like this, we have the 400 nanotesla storm there, and we see aurora there, but we have a 50 nanotesla storm there, which affect the SpaceX satellites, and that's due to the thermosphere, like a neutral density enhancement, the satellite track. So all these effects are different and they are independent of the like the indices. As typically mentioned, all these things like that matter most, like the satellite track, like the and all these things have been observed in the CIR based storm, where the storm was kind of one like a 50 to 150 nanotesla. So that storms also matter a lot, where a significant change been observed in ionosphere and thermosphere, which is responsible for these technological impacts. And then about the particle precipitation, it is not necessary like if it is a 400 nanotesla storm is there, but the precipitation will results or the particle flux that we observe at kind of the 6RE that we care most, like a geosynchronous orbit where our most satellites are there. But it depends. It depends on whether the characteristics of the storm, whether it depends on like whether all these couplings, like how is the space states was there, the how was the storm, how it whether it's carrying the SCPs along it, and a lot of thing, and that's been challenged in front of us. That's my comment.
Yeah, I would like to add, like directly to Pratik's question. You mentioned about that 2024 May super geomagnetic storm. There are a couple of papers which talk about how that storm impacted the people on the earth. They talk about like budget wise. I was searching for that paper to put the link in the chat box, but right now I'm not able to find that. But they talk about how the agriculture and most probably over the like the high latitude area, they got impacted during that storm. So not here. Even I asked the same question to NOAA people. There was a conference about it. I asked that what damage happened to Earth during this time, particularly during this storm. So during that time, this paper was published just 1 week before to that conference, and so since I'm not able to find it at the moment, what I will Just take my words. Even today, with the advance of the technology, but still we are impacted by the storms, particularly in the high latitude zone. Yeah. And rightly Kolpes mentioned the SpaceX. It was in, I think, 2022, 2023. It was a minor geomagnetic storm. And during that time, SpaceX launched the satellites and they got missed. So that also happened. And uh, these GIC, if you remember, Kolpes, about
Mm.
the GIC current system, they got affected in the mostly in the high latitude zone, but not in the equatorial. So those are like few things that came to my mind immediately. Okay.
Zubair has raised his hand.
Zubair.
Yeah. So just in continuous with the discussion, uh, I have been working in this direction a little bit since several years and attended several conferences and talks. Everyone talk about like BG is very important for geomedical storm. BG is very important for geomedical storms everywhere, anywhere, in model simulation, everywhere. But there are evidences which shows that uh, a CME with 20 nanotesla BG negative is causing very high intense storm, and CME with minus 50 nanotesla with BG is causing very minor storm. And their impact varies as we discuss here. So my question is like, does it like really VG amplitude is taking important role, or it's like a duration of the event, like how long your BG is negative? First question is this one. And when we talk about impact of in different perspective, so I always wonder, why one event is causing nothing, very strong event, nothing. CME speed is 800 kilometer, BG is very intense, and everything is very, very high, but you do not observe any major effect on the Earth. So I was wondering, many times I wondered, like, there is something more than that. We need to think about it. And it is not BG, it is not convective electric field. There is more than that. And what is more than that? I I think is like it is hidden somewhere in between this large scale phenomena, which Kalpesh and many people mention over here, like CME deformation, all those things. These are like large scale phenomena. But my personal feeling is like there is thing which is hidden is like between this large scale and kinetic scale domain. I mean something which is happening internally within the CME, for example, it can be very large scale current shoots, which is over there. Okay. And that enhances the reconnection at the daytime. And there can be different kind of local structure within the CME, which can be there, which increases or decreases your energy input into the matter sphere. And that small scale process doesn't care about like what is your CME, how big, how small it is. It is totally local phenomena. And it happens when the CME evolves in the solar wind. And different models and simulation do not count this kind of thing. If you talk about like Pratik is very aware of this simulation and modeling. So everyone do MHD kind of things, how the theme is evolving and contracting, deflecting, and all those things. But exactly what is happening within the CME, none of the model and simulation talk about it. And that's why if you look into the closely, so CME identical feature causing different effect and different profile of the storm and effect on the ionosphere. Why it is so? So that means it is not like global configuration effect. It is something in there like kinetic and mesoscale phenomena, which is within the CME and which leads to different energetics. I will say cross-scale coupling, either increase or decrease depending upon like orientation of the Earth as well as the orientation of that structure within CM itself. That's what I feel it. But yes, there are a lot of challenges, but we need to think something in this direction, which people generally, the solar guys who are doing solar physics like simulation and observation, they do not care about it, like what's going on. But picture is somewhere over there.
My first the first thing that came in my mind was that what about the velocity and density? Were they same in those events, or they were different?
Identical, I'm say same density, same
Same
velocity.
set.
Yeah,
Okay,
yeah,
okay. So everything is same. Dynamic pressure is same. BZ magnitude is same.
yeah,
So yeah, I think we need expertise where we are coupling the ionosphere, inner magnetosphere, outer magnetosphere. Maybe Sersho can comment on this because I have heard. I'm not an expert of this field, but the reconnection that happens in the backside, those are sometimes more important than the configuration in the day side.
yeah.
And if it is something going backward, then preconditioning also becomes super important. What was the setup just before the plasma or CME came, and then the night side reconnection happened? Sure. Do you want to
Yes,
add anything?
exactly. So, as Zubair mentioned, that identical storm time conditions and all these things, they might also like result in different types of configuration from the night side too. So, for example, like I have compared like two storms. One was the May storm, and the second one is the November storm of 2025. So the IMF BZ and all these things were more or less similar, but the night side conditions were drastically different. For example, one for the May storm, we could see the dipolarization fronts and all this mesoscale structure coming from the night side, and they are like they have these signatures on the ionospheric field aligned currents too. So they're like some small scale localization of intensity in the field aligned currents in the ionosphere due to those bulk flows coming from the night side. But that is completely absent in the next one, the next storm that I was talking about, so November storm. And this was also observed in the AL, like the westward electrojet and the AL indices for this particular for these two storms. So I feel that yes, there is nonlinearity between the things, that what is happening on the day side and what is the solar wind condition at the L1, and what is like their effect on the night side and on the inner magnetosphere. That is true, and like in like detailed modeling for the inner magnetosphere is necessary for that as well. And
Yeah, yeah.
yes.
Continue. Yeah, I
was,
completely. Yeah, Kalpesh, go
yeah.
ahead.
So I will also try, like, as you mentioned, your first question, whether the busy strength and the busy duration matter. Yes, both of the things matters. And the second thing about that, you talk whether the both storms with the same thing, same interplanetary conditions, and that results as yesterday, Dibbendu Chakravarti from PRL, he mentioned like it's system of systems. Like everything that matters, and as now Shirsha also mentioned, like everything like the internal state of the geospace, the preconditioning, and that a lot of things also came here in a picture. And the third thing that you mentioned about the model specifically, like MHD model or the kinetic or hybrid model, each model behaves differently. Like for example, like if we talk about the reconnection things, the energy flux that comes with the reconnection, the hybrid models, like those have the kinetic efforts, they work nice. But if we are talking with the large scale convection and large scale things, the MHD models are still better. So it's dependent what kind of things that we want to look, then we need to take that kind of glasses. And yeah, it's out there.
Yes.
Okay. Yeah, thanks for this nice discussion. Actually, this was helpful to understand the interdisciplinary, like how the magnetosphere ionosphere coupling and the interplanetary medium along with the solar dynamics, how these are intercoupled, and we have many more things that we need to understand actually at the fundamental level, and the prediction looks little far. But anyway, so thanks. Let us thank those two speakers of this session who presented, and all the participants who listened to this and participated in the discussion. Thank you, everyone.
Yeah,
This
thanks all.
concludes this session.